awe and wonder. Space, a vast, endless ocean of mysteries that stretches far beyond our complete comprehension. The universe, in all its grandeur, is a realm where the impossible becomes possible, and the unimaginable exists within plain sight. Stars, planets, galaxies, black holes, each a chapter in a cosmic story that has been unfolding for billions of years. We, here on Earth, are but a fleeting part of this grand tale, a part that, despite its brevity, is curious enough to look beyond the horizon and ask, what else is out there? The universe is far more immense than we can truly grasp. It contains more stars than all the grains of sand on Earth, an inconceivable number that sparks a deeper question. What else, in this vast sea of stars, remains hidden from our view? We know that the universe is expanding, growing larger with each passing second, sending galaxies away from us at speeds so fast that it feels like time itself is accelerating. How far does it stretch? Does it ever stop? What lies beyond the limits of our perception? We will journey through time and space, uncovering cosmic truths, ancient discoveries, and new breakthroughs that continue to shape our understanding of this great universe. Throughout the next hours, we will explore the stories of stars, galaxies, planets, and black holes. We will dive deep into the very fabric of the cosmos, discovering facts so extraordinary that they could only belong to the great unknown that stretches across the heavens. This journey is not one of speed or haste. It is a slow, deliberate exploration, a gentle drift through the universe, giving you time to absorb each piece of the story. As the miles of space pass by, you will feel the calming rhythm of knowledge settling in, easing your mind while expanding your understanding of the cosmos. In this video, we will look at the wonders of space through the lens of both the beginner and the expert. Whether you are familiar with the stars or seeing them for the first time, there will be something here for you to learn, something to intrigue you, something to marvel at. Our exploration begins with the very fabric of the universe itself. We will start with the question that has driven generations of astronomers, philosophers, and dreamers alike. What is the universe made of? When you consider the sheer number of stars that adorn the sky, one fact stands out above all others. There are more stars in the universe than all the grains of sand on every beach on Earth. When you hear this, it feels almost impossible to process. How can there be so many stars? And even more mind-boggling, what about the space between those stars, the vast stretches of nothingness? What is that? The universe contains roughly 100 billion galaxies. Each of those galaxies holds billions, sometimes hundreds of billions, of stars. And those stars? They are scattered across light years of space, an immeasurable distance. The scale of the universe is so immense that even trying to measure it feels like counting the moments of time that have passed since the beginning of everything. In the great expanse of space, the distances between galaxies continue to grow, and with them, the realization that the universe is not only vast, but expanding faster than we can keep up. You see, the very fabric of space itself is stretching. Galaxies are racing away from each other at incredible speeds, and this phenomenon has been happening ever since the universe began. You may have heard the term Big Bang, but do you truly understand what it means? This moment, this explosion of energy and matter, set the stage for everything that exists today. It marked the birth of space, time, and the very foundation of our universe. But the most fascinating part of this discovery is that the Big Bang is not just an event from the past. It is an ongoing process. The universe is still expanding today, right before our eyes. With this in mind, let us ask ourselves, what does it all mean? What is this great, infinite expanse of stars and galaxies telling us? Are we simply small specks in the order of things? Or are we part of something far greater? We know, thanks to the work of scientists like Edwin Hubble, that the universe is constantly changing. Hubble's observations of distant galaxies revealed that they were all moving away from us, a discovery that led to the understanding that the universe itself was expanding. This finding shattered long-held assumptions and unlocked a new era of scientific exploration. Yet, there is still so much we don't know about the universe. For instance, did you know that most of the universe is invisible to us? There is an enormous amount of matter and energy out there, mysterious forces that we can't directly observe. These unseen entities, dark matter and dark energy, make up more than 95% of the universe. Despite their dominance, we still don't fully understand them. What do they look like? How do they work? And what impact do they have on everything we see and feel? Now, take a moment to consider this. The universe is filled with superclusters of galaxies. The Hercules Corona Borealis Great Wall, the largest known structure in the universe, stretches an unbelievable 10 billion light-years across. It is a vast wall of galaxies that dwarfs anything we can visualize on Earth. These gigantic structures serve as a reminder of how small we are in the grand scheme of things. Yet they also stand as a testament to the power of cosmic forces. Even closer to home, we find wonders that continue to captivate and confuse us. Our own Milky Way galaxy is home to a supermassive black hole at its center, Sagittarius A star. This black hole, weighing millions of times more than our Sun, is an area of intense gravitational pull, devouring anything that ventures too close. But what happens inside a black hole? Once you cross the event horizon, it is as though time itself disappears, and we are left to wonder. Can anything truly escape the grasp of a black hole? Can anything survive beyond the point of no return? This journey, however, will not be a mere collection of facts and figures. Instead, we will delve into the heart of space exploration. From the first telescopic observations to the launch of human missions into the cosmos, humanity has long sought to understand the stars. Our curiosity drives us to look beyond the Earth, across the expanse of space, to uncover the secrets hidden in the heavens. As we embark on this exploration, we will touch on the many marvels that exist in space. Did you know that a day on Venus is longer than a year? Or that Mars, the red planet, has sunsets that are blue, due to the fine dust in its thin atmosphere scattering the sunlight? Each planet in our solar system has a unique characteristic, from Jupiter's great red spot, a storm raging for centuries, to Saturn's magnificent rings, which, though incredibly beautiful, are only a few kilometers thick. These are just a few of the mind-boggling facts we will explore. Our journey will take us across the vastness of space, from the smallest particles to the largest galaxies, exploring the wonders of the universe that continue to captivate our imagination and expand our knowledge. Each discovery will build upon the last, taking us deeper into the mysteries that surround us. Throughout this video, we will strive to keep things simple yet profound, focusing on the awe and wonder that space inspires. As we continue our journey, remember, this is not just about learning facts. This is about feeling the magnitude of the universe. Let it wash over you, and know that, no matter how far we travel, we are only just beginning to scratch the surface of the mysteries that lie in the stars. Chapter 1. The Cosmic Scale, a Universe Beyond Our Comprehension. The universe's boundless reach. Number of stars in the universe. The universe, an endless expanse, incomprehensibly vast, where each star is a distant sun and each galaxy a vast city of stars. But even that description doesn't fully do it justice. There are more than 100 billion galaxies in the universe, each one containing hundreds of billions of stars. These stars range from the dimmest red dwarfs to the brightest supergiants, shining their light across distances that defy understanding. The sheer number of stars, so many that we struggle to count them, each one a light year away, begs the question: how far can this universe extend? And how much of it is left for us to discover? When we peer into the deep sky, we're not simply observing distant objects. We're looking back in time. The light from stars travels at such a pace that what we see is often their past. When you observe a star 10 light years away, you're seeing what that star looked like a decade ago. Some of the stars we see in the night sky are no longer there. Their light traveled toward us, but the star itself may have already died, exploded, or faded into nothingness. As we continue our journey through space, consider this: each of these 100 billion galaxies has its own history, its own evolution. Some galaxies are small, with just a handful of stars, while others, like the Milky Way, have hundreds of billions of stars. The Milky Way, our home galaxy, is a massive spiral, with arms of stars, nebulae, and dust stretching outward. But even our galaxy, one of the larger ones, is just a speck in the grand mosaic of the universe. Now, consider that the stars in these galaxies are not solitary beings. Many stars are born in clusters, forming families of stars that share a common origin. These star clusters can be as small as a few stars, or as large as thousands, all bound together by gravity. Some stars live in binary systems, orbiting one another in an intricate dance, while others exist in groups of 3 or more. There are even larger structures, known as star nurseries, where new stars are born from clouds of gas and dust. The size of these star systems is mind-boggling. The nearest star to us, Proxima Centauri, is over 4 light-years away. A single light-year is nearly 9.5 trillion kilometers. To put that in perspective, the distance between Earth and the Sun is about 150 million kilometers, just 1 light-hour away. So when we think of our nearest star neighbor, the distance is an almost unfathomable 40 trillion kilometers. And while our Sun feels so immense to us, compared to some of the larger stars in the universe, it is small. Take Betelgeuse, a red supergiant star located in the constellation Orion. It is so large that if it were placed at the center of our solar system, its outer edges would extend beyond the orbit of Mars. That's the size difference between our Sun and just one of the stars in our galaxy. There are stars that are even more massive, stars that outshine our Sun by millions of times. These hypergiants, though far rarer, burn through their fuel at a rapid pace, living fast and dying young. When they finally run out of fuel, they explode in supernovae, one of the most powerful explosions in the universe. This is how many of the elements we find in the Earth's crust, elements like gold, silver, and iron, were created, scattered across space when these stars died. But stars don't just live and die in isolation. They are part of the ever-evolving structure of the universe. Galaxies themselves are not static. They grow, collide, and merge with other galaxies. Some galaxies, like the Andromeda Galaxy, are on a collision course with our own. In about 4 billion years, the Andromeda Galaxy and the Milky Way will collide, their stars passing through each other without touching, but the gravitational forces will reshape both galaxies. This collision, which may seem violent, is actually a normal part of the life cycle of galaxies. After the collision, new stars will form, born from the gas and dust that were once part of the merging galaxies. As we take in this vast scale, we must also consider the space between stars. The distance between them is so great that the idea of traveling from one star to another feels impossible. Yet, this empty space is not truly empty. It is filled with cosmic radiation, interstellar dust, and occasional rogue asteroids or comets. This space is not silent either. It hums with the vibrations of distant stars and the remnants of dead stars, all traveling through space at unimaginable speeds. Even the space within our solar system, which feels familiar to us, is immense. The distance between Earth and the Sun is 150 million kilometers, what we call an astronomical unit. Yet, even at that scale, the Sun is but one of billions of stars in our galaxy, and our galaxy is just one of billions in the universe. The scale of this universe is so far beyond human comprehension that it can be hard to wrap our minds around. Each galaxy, each star, is a piece of a cosmic puzzle, a puzzle so large that we may never know its full picture. Some galaxies are caught in the act of formation, swirling clouds of gas collapsing under their own gravity, birthing new stars, while others have already lived out their lifetimes, faded into darkness. Some galaxies are rich with stars, bursting with life and activity, while others are quiet, their stars slowly dying one by one. As we continue to study the stars, we uncover new revelations about the universe and its origins. We learn that stars form in clusters and that galaxies, despite their vast distances from each other, are interconnected by the very fabric of space itself. The story of the stars is not just the story of individual points of light. It is the story of the entire universe, how it has changed and evolved over billions of years. With each new discovery, we push the boundaries of what we know. The more we learn about the stars and galaxies, the more we understand about our place in this vast, incredible universe. And even as we gather knowledge, new questions arise, mysteries unfold, and new paths open up for exploration. We may never fully understand the entire universe, but with each step, we bring ourselves closer to the awe-inspiring truth of what lies out there, beyond our planet, beyond our galaxy, beyond our comprehension. The comparison between the number of stars and grains of sand on Earth. The universe is vast beyond measure, beyond anything we can fully grasp. The sheer number of stars scattered across the cosmos is enough to make us pause and contemplate the unimaginable scale of space. Scientists estimate that there are over 100 billion galaxies in the universe, each one hosting hundreds of billions of stars. Every galaxy is a sprawling collection of celestial bodies, massive systems held together by gravity. Yet, when we think of all the stars in those galaxies, it is still just a small fraction of the cosmic puzzle. Now, here's a staggering thought. There are more stars in the universe than there are grains of sand on all of Earth's beaches. When you think about the vast stretches of sand, the seemingly endless expanse of beaches around the world, it's difficult to believe that the stars outnumber them. But this is the reality we face. The universe is teeming with light, a shining ocean of stars that stretches far beyond our ability to comprehend. Consider this: our own Milky Way galaxy alone contains over 200 billion stars. Yet, as enormous as the Milky Way is, it's just one of many. Our galaxy is merely a speck in the greater expanse of space, a member of a vast collection of galaxies that populate the universe like stars scattered across the night sky. And each of those galaxies has its own stars, each one a sun, some burning brightly, others fading into the distance. Let's break it down further. The number of stars in our galaxy alone, the Milky Way, could fill hundreds of books with their names, and that's just one galaxy. Multiply that by the 100 billion galaxies we believe exist in the universe, and you begin to understand the scale we're talking about. It's not just the number of stars that's incredible. It's the idea that all these stars exist within vast, interconnected webs of space, where distances stretch out in ways that are impossible to fully perceive. Think of the stars as a giant puzzle, with each one contributing its own unique story to the cosmic canvas. Some of these stars are younger, burning with fierce intensity, while others have already aged and become giants or even collapsed into black holes. The life cycles of stars are as varied as the stars themselves, from the birth of new stars in cosmic nurseries to the explosive death throes of massive stars that end their lives in supernovae, creating heavy elements that are scattered into space. The sheer volume of stars also leads us to a question. Why are there so many? What is their purpose in the grand design of the universe? Perhaps the answer lies in the fact that stars are the building blocks of everything in the universe. They are the forges where elements are created, elements that are essential to the formation of planets, moons, and even life itself. Every element that makes up our world, every atom in our bodies, was formed in the heart of a star, either during its lifetime or when it exploded in a supernova. But the stars themselves are not static. They don't remain in the same place forever. They move through space, sometimes alone, sometimes in clusters, and sometimes in galaxies. The concept of a moving star may seem strange, but it is true. These stars may seem fixed in place when we look at them from Earth, but they are constantly shifting, sometimes in small ways, sometimes in massive cosmic movements. Consider a star like our Sun. It is part of a vast cosmic dance. The Sun, along with the entire solar system, orbits around the center of the Milky Way galaxy. It takes the Sun about 225 million years to complete one full orbit around the center of the galaxy. This motion is so slow that we can't perceive it within a human lifetime, but it's happening all the same. As we look deeper into the universe, we see that these stars are not just part of individual galaxies. They are part of vast clusters and superclusters, groups of galaxies that are bound together by gravity. These immense structures stretch across billions of light years, serving as the largest known objects in the universe. The distances between the stars in these clusters are vast, but the stars themselves still interact with one another. Gravity pulls them together, sometimes causing them to collide and merge, creating new stars in the process. These galactic clusters, as massive as they are only part of the story. There are also the empty spaces between them, the voids. These expanses of nothingness might seem to be empty, but even in these voids, space is filled with dark matter, an invisible substance that makes up most of the universe's mass. Dark matter doesn't emit light, nor can we see it directly, but we know it exists because of its gravitational influence on galaxies and galaxy clusters. Dark matter isn't the only mysterious component of the universe. There's also dark energy, a force that is driving the accelerated expansion of the universe. We don't fully understand it, but we know that it constitutes about 68% of the universe's energy content. It's yet another element of the cosmic puzzle that remains largely unknown, pushing us to continue exploring and seeking answers to the questions it raises. This enormous scale is difficult for the human mind to fully process. How can we possibly wrap our heads around numbers that are so large, distances that are so vast, and phenomena so distant from our experience? We try to use our best tools, telescopes, math, models to bring the universe closer, but the truth is we are still limited by our own perspective. But that doesn't make space any less fascinating. Instead, it only deepens the mystery, urging us to learn more. The more we understand about the stars, the more we realize just how much is left to discover. And that, perhaps, is the most incredible aspect of all. The universe is so vast, so full of wonders, that we can only scratch the surface of its mysteries. In the end, we are left with this incredible truth. The universe is full of stars, more stars than we could ever count. And each one has a story to tell, a piece of the grand cosmic narrative. Some of those stars are still being born. Others are on the brink of their final moments. Some shine brightly, their light traveling through the cosmos for millions of years before it reaches our eyes. Each one of these stars is part of a larger picture, a picture that continues to evolve, one that we are only just beginning to understand. The universe, vast and ever-changing, is a place of awe. The stars that fill it are a testament to the power, the beauty, and the mystery that exists beyond our world. And though we may never fully understand everything about the cosmos, the very act of exploring it allows us to glimpse into something far greater than ourselves. The expansion of the universe. The universe is not a static entity. It is a living, breathing expanse, constantly shifting and changing. And at the heart of its ever-changing nature lies a force so powerful that it is shaping the very fabric of space itself, the expansion of the universe. From the moment the universe began with the Big Bang, around 13.8 billion years ago, it has been expanding. What does this mean? Imagine everything in the universe. Galaxies, stars, dust, and dark matter, all packed into a space so small that it defies understanding. Then, in an instant, the universe began to grow, rapidly expanding from a single, incredibly dense point. The energy released in this expansion created the universe we know today, but it didn't stop there. The universe continues to expand, and not just at a steady rate. It is accelerating. This means that the distance between galaxies is growing faster than ever before. You might be wondering how that's possible, considering how vast the distances already are. The key lies in the fabric of space itself. Space isn't merely a container for objects. It can stretch, expand, and contract. The galaxies, in a sense, aren't moving through space like cars on a road. Rather, the space between them is growing, stretching further and further as time passes. This expansion isn't something that can be observed directly in the same way we observe the motion of a car or a planet. It's happening on a cosmic scale, affecting distances measured in light years, distances so vast that they are beyond the reach of our daily comprehension. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers, a distance that seems almost absurd in its size. But galaxies are moving apart at speeds that are even more astonishing. The most surprising part of this expansion is that the universe's rate of growth is accelerating. It isn't just growing, it's speeding up. This discovery shocked scientists because it was believed that gravity, the force that pulls things together, would slow the universe's expansion over time. But instead, something else is at work. This mysterious force, which we call dark energy, is driving the accelerated expansion of the universe. Dark energy is a puzzling and still poorly understood force, but its impact is undeniable. It makes up about 68% of the universe, and without it, the universe would be slowing down, not speeding up. The idea of a force that pushes galaxies apart sounds strange, yet it is this force that is dictating the ultimate fate of the universe. Dark energy's influence is so powerful that it's overcoming gravity, and as a result, galaxies are moving away from one another at an increasing rate. You might be wondering how fast galaxies are receding from us. In some regions of the universe, galaxies are moving away at speeds of millions of kilometers per hour. This might sound like an enormous speed, but it's not just the movement of individual stars or planets we are talking about. It's entire galaxies with billions of stars spreading out across the universe, pulled apart by the very nature of space itself. But what does all this mean for the future of the universe? As galaxies drift apart, the night sky will look dramatically different in the distant future. Over billions of years, galaxies will continue to move farther away from us. Some will escape the pull of gravity entirely and be lost to the cosmic void. Other galaxies, like our own Milky Way, will eventually collide with nearby galaxies, but even these will eventually be stretched apart as the force of expansion continues to grow. For now, we are in an era where the expansion of the universe is still a force we can observe. We can measure it through the light from distant galaxies. The farther away a galaxy is, the faster it is receding from us, due to the stretching of space between us and them. This is one of the many profound ways in which the universe defies our normal understanding. We tend to think of space as a fixed stage on which the events of the universe unfold, but in reality, space itself is dynamic. It stretches and bends, carrying galaxies along with it. If you were to stand on a distant galaxy and look back at the Milky Way, you would see us moving away from you at a similar speed. From every corner of the universe, galaxies are moving away from one another, as if we are all part of a grand cosmic dance, and the music is playing faster and faster. The universe is growing larger and larger, with no sign of slowing down. This expansion brings with it a set of questions about the ultimate fate of the universe. Will it continue expanding forever? Will the forces that cause this acceleration eventually lead to a dramatic end? A fate where galaxies are so far apart that they are no longer visible to each other, leaving behind a cold, dark universe? Or will something else intervene, altering the course of expansion once again? These questions remain unanswered for now, but they highlight the extraordinary nature of the universe. The fact that the universe is not only expanding but doing so at an accelerating rate is a testament to the sheer power and complexity of the forces at work in the cosmos. The expansion of the universe is not just a scientific fact. It is a mystery that continues to unravel, leading us to new understandings about space, time, and the very nature of reality itself. So, as galaxies move further away from each other, as the space between them stretches and grows, we are reminded of the immense scale of the universe. It is a universe constantly on the move, a universe that will never stop expanding, a universe full of mysteries and surprises yet to be discovered. As we continue to probe deeper into the fabric of space, the questions will multiply. And with each answer, the universe will reveal even more layers, each one more mind-boggling than the last. The expansion of the universe isn't just a phenomenon. It is a constant reminder that the cosmos is alive, dynamic, and ever-evolving. It beckons us to continue our exploration, pushing the boundaries of human knowledge as we venture further into the unknown. And though we may never fully grasp its full extent, the mere pursuit of understanding is an adventure that will continue to unfold, just as the universe itself continues to stretch outward, expanding at an accelerating rate. The story of Edwin Hubble's discovery of the expanding universe. In the early 20th century, the world of astronomy was on the brink of a monumental discovery. For centuries, humans gazed up at the stars and wondered about their place in the vastness of space. Our understanding of the universe was largely static, shaped by the belief that our galaxy, the Milky Way, was the entire universe. It was a small, contained view of reality. But that all changed when one man, with a sharp eye and a daring approach, uncovered a truth that would forever alter our view of the cosmos. That man was Edwin Hubble, an astronomer whose work in the 1920s changed everything we thought we knew about the universe. Prior to Hubble, many astronomers believed that the Milky Way was the entire universe, with other nebulae seen in the sky thought to be distant, cloud-like structures within our own galaxy. But Hubble's work would show that these nebulae were actually entire galaxies, each containing billions of stars, just like our own. This realization opened the door to a universe far larger than anyone had imagined. In 1924, Hubble turned his attention to the Andromeda Nebula, which had long been thought of as a mere cloud of gas and dust. By analyzing the light coming from it, Hubble was able to determine that the Andromeda Nebula was, in fact, a galaxy. This discovery proved that our Milky Way was not the only galaxy in existence, and that the universe was not a small, static place but a vast expanse, filled with countless galaxies. But Hubble's groundbreaking discoveries didn't stop there. As he continued to observe galaxies at greater distances, he made an even more profound realization. He noticed that the farther away a galaxy was, the faster it appeared to be moving away from us. This observation became known as Hubble's law. Simply put, it meant that galaxies were receding from one another, and the further away a galaxy was, the faster it was moving. This discovery was the first piece of evidence that the universe itself was expanding. Hubble's law challenged the prevailing view of the time. Prior to this, scientists believed the universe was static and unchanging. Hubble's observations proved that the universe was, in fact, in constant motion, with galaxies stretching farther apart as time went on. This was the beginning of the realization that the universe had a history, a beginning, and perhaps an end. The implications of this discovery were profound. If galaxies were moving away from one another, it suggested that the universe had started from a single point. This idea, combined with the concept of a continuously expanding universe, led to the development of the Big Bang theory. According to this theory, the universe began as an infinitely small, hot, and dense point and has been expanding ever since. The evidence for this idea, once largely speculative, was now backed by Hubble's data. For Hubble, this was more than just a scientific breakthrough, it was a paradigm shift. It reshaped the way we viewed the cosmos. No longer was the universe seen as a collection of fixed stars and static galaxies. Instead, it was a dynamic, ever-expanding expanse, in which galaxies were racing apart, pushed by an invisible force that we would later come to understand as the expansion of space itself. Hubble's discovery also had another far-reaching implication. It brought the possibility of a beginning of the universe into sharp focus. If galaxies were moving apart, that meant they must have all been closer together at some point in the distant past. The idea that the universe had a starting point was a radical shift in thinking, one that would eventually lead to the development of the Big Bang theory. For the first time, scientists were considering that the universe might not have always been here in its current form, that it had a beginning and perhaps an end. This concept of an expanding universe challenged the idea of a static, eternal cosmos and forced humanity to confront the true nature of the universe. The implications of this discovery went far beyond astronomy, touched on questions about the origin of everything. What happened at the beginning? Was the universe always expanding, or did it have a starting point? How did time itself begin? As scientists studied Hubble's findings, they began to unravel more mysteries. They discovered that the rate at which the universe was expanding was itself changing over time. The realization that galaxies were not just moving away from one another, but accelerating in their movement suggested the presence of an unknown force, later identified as dark energy, that was driving the accelerated expansion of the universe. This was a puzzle that would take decades to begin solving. Hubble's discoveries also sparked a wave of new research into the nature of galaxies, the structure of the universe, and the potential for life elsewhere in the cosmos. By proving that galaxies existed beyond the Milky Way and that the universe was expanding, Hubble opened the doors to a new era in astronomy. His work laid the foundation for modern cosmology, the study of the universe as a whole, and prompted a shift from thinking of the cosmos as a fixed, unchanging place to recognizing it as a vast, dynamic, and evolving entity. What Hubble achieved wasn't just about counting galaxies or measuring their speed. It was about understanding our place in a universe that is vast, ever-changing, and full of mysteries. His discoveries forced us to confront our own smallness in the grand scheme of things, and to ask questions about our place in an ever-expanding universe. Hubble's legacy lives on in every corner of modern astronomy. From the Hubble Space Telescope, which bears his name, to the study of dark energy and the search for the farthest galaxies, his work continues to shape our understanding of the universe. It serves as a reminder that, despite all our progress, we are still only beginning to understand the incredible scale, complexity, and mystery of the cosmos. As we move forward in our exploration of the universe, Hubble's discoveries remain a touchstone, guiding us as we continue to ask the most fundamental questions about the nature of space, time, and the universe itself. His work opened our eyes to a universe that is far larger, more dynamic, and more mysterious than we could have ever imagined, and it continues to inspire the generations of astronomers who seek to uncover the secrets of the cosmos. Mysterious components, dark matter and dark energy. The universe, as we know it, is far more complex than we could ever have imagined. When we look up at the night sky, we see only a fraction of what exists in the vast expanse of space. The visible matter, everything from stars to planets to galaxies, makes up just a small portion of the cosmos. In fact, more than 95% of the universe is completely invisible to us. This vast, hidden realm is composed of two enigmatic forces, dark matter and dark energy. Let's start with dark matter. Despite the name, dark matter isn't actually dark in the way we think of darkness. It doesn't emit light or energy, and it's completely undetectable by the instruments we currently have. But it's there, and its presence is undeniable. While we can't see it, we can observe its influence through the gravitational pull it exerts on the galaxies and clusters of galaxies around it. It's like an invisible hand, guiding the motions of objects in space. Dark matter makes up about 27% of the universe, but it is not something we can observe directly. Instead, its existence is inferred from the behavior of galaxies. For instance, when we observe how galaxies rotate, something doesn't add up. The stars within galaxies should be moving much faster than they are, given the visible matter that we can see. But they aren't. There must be something invisible, something exerting an additional gravitational pull, which slows the stars down. That invisible something is dark matter. This same invisible matter also helps to explain why galaxies are not flying apart. The amount of visible matter in a galaxy is not enough to hold it together. Yet, when we examine galaxies, we see that they remain intact, orbiting each other and remaining in a stable structure. This could only be possible if there is more matter we cannot see, dark matter. It holds the galaxy together, forming a hidden scaffolding that keeps everything from spinning apart. Now, as if dark matter wasn't elusive enough, there's another force, even more mysterious: dark energy. Dark energy is even more difficult to study and understand than dark matter. This strange force is thought to make up roughly 68% of the universe. Its presence is known through its effect on the expansion of the universe. The universe, as we discussed earlier, is expanding, and this expansion is not slowing down as we might have expected. Instead, the rate of expansion is accelerating. Something, or rather some force, is pushing galaxies away from each other at increasing speeds. This is where dark energy comes in. It is believed that dark energy is the driving force behind the accelerated expansion of the universe. While we don't know exactly what dark energy is, we can see its effects. It's as if there's an invisible force stretching space itself, pushing galaxies farther apart and altering the way the universe evolves. Unlike dark matter, which works through gravity and pulls things together, dark energy seems to push things apart, counteracting the force of gravity. This creates a tension in the universe, one that may eventually lead to dramatic changes in the cosmos. If dark energy continues to accelerate the expansion of the universe, it could ultimately cause galaxies to be so far apart that they will no longer be able to interact with one another. The universe could reach a point where the stars and galaxies we see today will be completely isolated, drifting endlessly in an ever-expanding void. The effects of dark matter and dark energy are deeply woven into the fabric of the universe, and though we may not fully understand them, they shape the universe's evolution. The universe is not just expanding. It is accelerating, stretching at a pace that seems to defy all logic. Scientists have been working tirelessly to better understand these forces, but as of now, much of dark matter and dark energy remains a mystery. Their presence is known through their influence on the galaxies, on clusters of galaxies, and on the very structure of the universe itself. But what is the true nature of dark matter and dark energy? How do they fit into the overall story of the universe? These questions remain at the frontier of scientific inquiry, and while we may not yet have the answers, the search for them drives much of modern cosmology. The mysteries of dark matter and dark energy could hold the key to understanding the universe's past, present, and future. Perhaps, as we advance in our exploration of the cosmos, we will uncover more clues that will help us unlock the secrets of these invisible forces. For now, however, dark matter and dark energy remain two of the greatest unsolved mysteries in the universe. They are the unseen architects of the cosmos, shaping the galaxies, holding them together, and pushing them apart, all from the shadows. Their presence is subtle, but their impact is immense. As we continue to gaze into the depths of space, we find ourselves faced with a fundamental truth. There is so much more to the universe than meets the eye. The vast majority of the cosmos is hidden from us, waiting for the next generation of scientists to peer into its depths and uncover the forces that govern it. The concept of gravitational lensing. In the universe, some things are hidden in plain sight. We know they are there, but we can't see them directly. One such mystery is dark matter, that invisible, elusive substance that makes up a significant portion of the universe. But how do we study something that can't be observed with traditional instruments? The answer lies in a phenomenon known as gravitational lensing. Gravitational lensing occurs when a massive object, like a galaxy or cluster of galaxies, bends and distorts the light from objects behind it. This bending is not some optical illusion. It's a direct consequence of Einstein's theory of general relativity, which tells us that massive objects warp. The light from distant stars or galaxies passes near a massive object, and because space itself is curved, the light is bent, much like the way a magnifying glass bends light to focus it. This is where things get interesting. Because dark matter is invisible, we can't see it directly. But the gravity from dark matter can still bend light. In fact, scientists can use this bending of light as a tool to map the distribution of dark matter. When light from a distant galaxy passes through a massive cluster of galaxies, which contains dark matter, the path of that light is distorted. The result is that the distant galaxy appears stretched, distorted, or even duplicated. This effect allows scientists to see where dark matter is located, even though it can't be seen directly. By studying these distortions, researchers can map out the shape and density of dark matter in galaxy clusters. This phenomenon has allowed scientists to confirm that dark matter exists, and it has provided them with a glimpse into the structure of the universe in ways that were once impossible. By looking at how light is distorted as it passes through gravitational lensing, we can learn more about how dark matter is distributed throughout the universe, even though it remains invisible to our eyes. This method of studying dark matter isn't just theoretical, it's already yielding remarkable results. Some of the most distant galaxies are being studied through the lens of gravitational lensing. By focusing on these distortions in light, scientists can measure the mass of galaxy clusters and determine the amount of dark matter present in them. The more we study these cosmic lenses, the clearer the picture becomes of how dark matter affects the universe on the largest scales. Gravitational lensing also helps us explore the structure of the universe itself. We can look back into the past, to the time when the light from distant galaxies first began its journey toward us. Light from galaxies billions of light years away has traveled across the universe for immense stretches of time, and by observing it through gravitational lensing, we can look at the universe as it existed at the very dawn of its creation. These observations offer us a window into the past, allowing us to peer back to a time when galaxies were first forming. But gravitational lensing is not only about dark matter. It also provides us with an entirely new way of looking at the cosmos. It allows us to see objects that would otherwise be hidden from view, objects that are far too distant or faint to observe with traditional telescopes. Through the bending of light, we can reveal galaxies, stars, and clusters that would otherwise remain invisible. The universe is not just a static thing, but an active, dynamic entity. Every galaxy, every star, is part of an intricate web that connects everything. And with gravitational lensing, we can study this web in new and exciting ways. The power of gravitational lensing is that it opens the door to unseen worlds. As we continue to develop more advanced telescopes and techniques, our ability to study these hidden aspects of the universe will only grow. By studying how light bends around massive objects, we will uncover more about the mysterious substances that shape the cosmos, like dark matter and dark energy, and learn how these forces shape the evolution of the universe itself. Through gravitational lensing, we are learning more about the universe than we could have imagined. It is a powerful tool that allows us to peer into the hidden depths of space, revealing the invisible forces that govern the universe. It is through this phenomenon that we continue to uncover the mysteries of the cosmos, moving ever closer to understanding the vast, complex, and beautiful universe in which we live. The largest structures in the universe, the Hercules Corona Borealis Great Wall. In the immense expanse of the cosmos, we are constantly discovering structures that challenge our understanding of what is possible. The universe is full of wonders, and among the most awe-inspiring of them all is the Hercules Corona Borealis Great Wall, the largest known superstructure in the universe. This colossal formation stretches across a mind-boggling 10 billion light-years, making it one of the most immense objects we have ever discovered. A light-year, for reference, is the distance that light travels in 1 year, about 9.46 trillion kilometers. So, when we say the Hercules Corona Borealis Great Wall spans 10 billion light-years, we are talking about a distance that is almost impossible to fathom. To put it in perspective, if you could travel at the speed of light, it would take you 10 billion years to traverse this massive structure, and that's only if you could somehow travel without ever stopping. The Hercules Corona Borealis Great Wall is not a single object. Rather, it's a vast supercluster of galaxies that are grouped together by the gravitational forces acting between them. This superstructure is so large that it challenges our fundamental understanding of the universe. It's a sprawling, interconnected network of galaxy clusters that stretches across space, connecting different parts of the universe like a vast web. And yet, as huge as this wall is, it is just one of many large-scale structures that make up the fabric of the universe. What makes the Hercules Corona Borealis Great Wall so extraordinary is not just its size, but its complexity. It's not just a collection of random galaxies. These galaxies are gravitationally bound, forming a structure that stretches across a vast region of the universe. It's as if the universe itself is organizing these galaxies into gigantic structures, creating vast interconnected walls that span across unimaginable distances. This superstructure was first discovered through the observation of the distribution of quasars. Quasars are the extremely bright and energetic centers of distant galaxies, powered by supermassive black holes. By studying the positions of these quasars, astronomers were able to map out the size and shape of the Hercules Corona Borealis Great Wall, revealing just how massive and complex this structure truly is. But despite its awe-inspiring size, the Hercules Corona Borealis Great Wall is just one example of the many large-scale structures in the universe. In fact, the universe is full of such superstructures, some even larger, stretching across even greater distances. These immense cosmic formations raise profound questions about the structure of the universe, its formation, and the forces at work shaping it. In the grand scale of things, the Hercules Corona Borealis Great Wall serves as a reminder of just how vast and interconnected the universe truly is. It is a testament to the incredible complexity of the cosmos, where galaxies are not isolated entities, but part of vast networks and structures that span unimaginable distances. It challenges us to think about the universe as something that is constantly in motion, constantly growing, and constantly evolving, shaped by forces we are still striving to understand. As we continue to explore the universe, the discovery of structures like the Hercules Corona Borealis Great Wall pushes the boundaries of our knowledge and invites us to imagine what else might be out there, waiting to be discovered. It reminds us that we are only just beginning to scratch the surface of the vast, interconnected universe that surrounds us, and that the more we learn, the more we realize how much more there is to uncover. The impact of the discovery of the Hercules Corona Borealis Great Wall. The discovery of the Hercules Corona Borealis Great Wall the largest known superstructure in the universe, stretching an unfathomable 10 billion light-years, did not just reveal a colossal physical structure. It fundamentally altered our understanding of the universe's formation. Before this discovery, our view of the cosmos was shaped by the idea that galaxies were relatively isolated entities, scattered in a seemingly random manner across the universe. But the Great Wall challenged that perception in the most extraordinary way possible. It showed us that the universe is not just a vast sea of galaxies floating in empty space. It is a highly structured, interconnected system, where galaxies form vast clusters and superclusters that are bound together by gravity, creating enormous cosmic structures that defy the imagination. When astronomers first identified the Hercules Corona Borealis Great Wall, they were forced to reconsider their assumptions about the distribution of matter in the universe. Previously, scientists had theorized that the universe was largely homogeneous on the largest scales. In other words, matter should be spread out relatively evenly, with only minor irregularities in the arrangement of galaxies. But the discovery of this enormous wall of galaxies shattered that model. Instead of a uniform, evenly distributed universe, we saw that the cosmos had a structure far more intricate and complex than anyone had imagined. This massive wall of galaxies revealed the universe to be a place of giant, interconnected webs of matter, a vast and dynamic tapestry where the large-scale structure is shaped by the forces of gravity and the interplay of cosmic energy. This discovery challenged scientists to think differently about the history and formation of the universe. The very idea that such colossal structures could exist at all forced them to question how the universe came to be in the first place. The Hercules Corona Borealis Great Wall provides a new clue in the puzzle of cosmic evolution, suggesting that the universe was never a static entity, but rather one that has been dynamically evolving over time. The formation of these immense structures can only be explained by the gravitational forces acting on matter, slowly pulling galaxies together over billions of years, forming superclusters like the Great Wall. Furthermore, the discovery of this massive superstructure suggests that the early universe was not uniform, as was once thought. Instead, it points to an early stage in the universe's evolution where matter began to clump together, forming the first galaxies, clusters, and superclusters. These clumps of matter grew over time, pulled together by gravity, gradually forming the vast structures we see today. This process of large-scale structure formation reveals that the universe has undergone a long history of cosmic evolution, marked by the constant interplay between gravitational forces, dark matter, and other cosmic elements. One of the most significant implications of this discovery is that it has reshaped our understanding of the universe's expansion. For years, the idea of an expanding universe has been central to our models of cosmology, suggesting that galaxies are moving apart as space itself stretches. But the discovery of structures like the Hercules Corona Borealis Great Wall implies that the expansion of the universe isn't happening uniformly. Instead, gravity has caused some regions of the universe to become more densely packed, leading to the formation of enormous structures, while other regions remain less populated, expanding at a faster rate. This discovery has led scientists to reconsider the role that gravity and dark matter play in shaping the universe, suggesting that the forces that control the universe's large-scale structure are far more complex than previously thought. The Hercules Corona Borealis Great Wall also gives us insight into the distribution of dark matter, an invisible substance that makes up most of the universe's mass. Dark matter is not something we can observe directly, but we can infer its presence by studying the movement of galaxies and the way they interact with one another. The mass of the Hercules Corona Borealis Great Wall, which is composed of both visible and dark matter, is far greater than what we can see. This has led to new theories about how dark matter influences the formation of large-scale structures. In essence, dark matter acts as the cosmic scaffolding, helping to hold these immense walls of galaxies together. The discovery of the Great Wall has profound implications for our understanding of the future of the universe. It suggests that the universe is not just expanding uniformly, but that it is filled with vast regions of dense, gravitationally bound matter. These superstructures are likely to play a significant role in the future evolution of the cosmos. As the universe continues to expand, the forces within these superclusters will influence the motion of galaxies, potentially leading to new formations and even mergers between galaxy clusters over billions of years. The Hercules Corona Borealis Great Wall is not just a snapshot of the universe at a particular moment in time, but a glimpse into the future. A future where cosmic structures evolve, interact, and transform. The impact of this discovery extends beyond our understanding of the universe's present and future. It has also reshaped our ideas about the very origins of the universe. The formation of large-scale structures like the Great Wall provides a new perspective on the early universe, showing that galaxies began to form much earlier than we once thought. This discovery has prompted scientists to re-examine models of the Big Bang and the early stages of cosmic evolution. The fact that such massive structures were able to form so early in the universe's history suggests that the processes of galaxy formation and large-scale structure development began far sooner than previously believed. In conclusion, the discovery of the Hercules Corona Borealis Great Wall has not just revealed the largest known superstructure in the universe. It has dramatically reshaped our understanding of the universe's formation, its structure, and its future. It challenges long-held assumptions, provides new insights into the distribution of matter, and opens up exciting new avenues for exploration. The Great Wall is a testament to the complexity and vastness of the cosmos, and it serves as a reminder that we are still only scratching the surface of the mysteries that lie beyond our reach. The universe is a far more intricate and dynamic place than we ever imagined, and with each new discovery, we come closer to understanding the true scale and nature of the cosmos. Chapter 2: Black Holes and the Cosmic Abyss. The Enigma of Black Holes. Black holes are among the most fascinating and mysterious objects in the universe. These regions of space are not just distant curiosities. They are some of the most extreme phenomena known to science. A black hole is defined as a region in space where the gravitational pull is so intense that not even light can escape. This means that once something enters a black hole, it is gone forever, unable to return. But despite the fearsome reputation they've gained, black holes are essential to understanding the structure of the universe. So, what exactly are black holes and how do they form? At their core, black holes are born when massive stars run out of fuel and collapse under their own gravity. When a star burns through its nuclear fuel, the outward pressure from the energy produced by fusion is no longer able to balance the immense gravitational force pulling inward. The star begins to collapse, compressing its core to an infinitely small point. This point is known as a singularity, and it is surrounded by the event horizon, the boundary beyond which nothing, not even light, can escape. However, for now, let's focus on how these black holes come into existence. There are three main types of black holes: stellar mass black holes, supermassive black holes, and intermediate black holes. Each one differs in size, formation process, and impact on its surroundings. Stellar mass black holes. Stellar mass black holes are the most common type. These black holes typically form when a star that is between 8 and 25 times the mass of our Sun reaches the end of its life. Once the star runs out of fuel, it collapses under its own gravity, creating a singularity. The core of the star contracts and becomes extremely dense, creating an object with an enormous amount of mass compressed into an incredibly small space. The resulting black hole can be several times more massive than the Sun, yet its size can be as small as a city. These black holes are often found in binary systems, where they orbit around a companion star, slowly pulling in matter and generating powerful radiation. The process of stellar collapse and the formation of stellar mass black holes is one of the most violent events in the universe. When a massive star collapses into a black hole, it often triggers a supernova, a violent explosion that releases enormous amounts of energy into space. This explosion can outshine an entire galaxy for a short time, making it visible across vast distances. The remaining core of the star after the explosion is what becomes the black hole. Supermassive black holes. Supermassive black holes, as the name suggests, are far larger than stellar mass black holes. These giants are believed to lie at the centers of most, if not all, large galaxies, including our own Milky Way. Supermassive black holes can have masses ranging from millions to billions of times the mass of our Sun. But how do they form? The answer isn't entirely clear, but there are several theories. Some scientists believe that supermassive black holes formed from the collapse of massive clouds of gas in the early universe. Others suggest that smaller black holes may have merged over time to grow into these giants. One of the most intriguing aspects of supermassive black holes is their role in the evolution of galaxies. These black holes are not just passive objects sitting at the centers of galaxies. They are active participants in shaping the galaxies themselves. The gravitational influence of a supermassive black hole affects the orbits of nearby stars, and the energy generated by the black hole can regulate star formation within the galaxy. In some cases, supermassive black holes can even produce powerful jets of energy and matter, known as relativistic jets, that shoot out into space at near-light speeds. The supermassive black hole at the center of our Milky Way, known as Sagittarius A*, is one of the most studied objects in the universe. Despite being millions of times more massive than the Sun, it doesn't seem to be actively consuming large amounts of matter at the moment. Instead, it seems to be in a relatively quiet phase, slowly pulling in surrounding gas and dust. But over the course of its life, it will continue to grow, possibly merging with other black holes or consuming vast amounts of material. Intermediate black holes. In between stellar mass black holes and supermassive black holes lies a mysterious category known as intermediate black holes. These black holes have masses ranging from hundreds to thousands of times that of the Sun. They are not as common as stellar mass black holes or as massive as supermassive black holes, but their existence challenges our understanding of black hole formation. The key question with intermediate black holes is how they form. One possibility is that they arise from the merger of smaller black holes or from the collapse of very massive stars in dense regions of space, such as star clusters. Another theory is that intermediate black holes could be the result of the accumulation of smaller black holes over time, in a process known as hierarchical merging. The discovery of intermediate black holes has been a major challenge for astronomers because they are difficult to detect. They are not as easy to spot as stellar mass black holes, which often interact with companion stars, nor are they as massive and bright as supermassive. However, recent advances in observational technology, particularly the detection of gravitational waves, have begun to reveal more about these elusive black holes. When two black holes merge, they create ripples in spacetime that can be detected by instruments like LIGO. These ripples, known as gravitational waves, provide us with a new way of studying black holes and their formation. The role of black holes in the universe. While black holes may seem like the ultimate destroyers of matter, they play a crucial role in the evolution of the universe. They are not just destructive forces. They are also engines of creation. Stellar mass black holes, for example, are often surrounded by accretion disks, hot, rotating clouds of gas and dust. As matter falls into the black hole, it heats up and releases enormous amounts of energy, which can light up the surrounding space. In the case of supermassive black holes, the energy produced by the accretion disk can power active galactic nuclei, bright regions at the center of galaxies that emit more energy than the rest of the galaxy combined. These black holes also influence the formation of new stars. The gravitational forces they exert on nearby stars can trigger the formation of new stars and planets, shaping the evolution of galaxies. In fact, without black holes, it's likely that galaxies would look very different today. They help to regulate the flow of matter, prevent galaxies from growing too large, and influence the rate of star formation. Ultimately, black holes are both the creators and destroyers of the universe. They shape the fabric of space and time, warp the paths of light, and act as cosmic factories, producing energy and matter as they consume the surrounding space. From stellar mass black holes that result from the death of stars to supermassive black holes at the hearts of galaxies, and the elusive intermediate black holes scattered throughout the cosmos, they are all part of the intricate cosmic dance that governs the universe's evolution. In the next chapters, we will delve deeper into the effects of black holes on their surroundings, particularly focusing on what happens when matter crosses the event horizon, the point of no return. But for now, we've only just begun to scratch the surface of understanding these enigmatic objects. As we continue to study black holes, we move closer to uncovering the secrets of the universe itself. The event horizon. As we venture deeper into the mysteries of black holes, we come to the most intriguing and terrifying feature of these cosmic giants: the event horizon. The event horizon marks the point of no return. Once something crosses this boundary, it is pulled inexorably toward the black hole singularity, its center, where gravity is infinitely strong, and the laws of physics as we know them break down. The event horizon is not a physical boundary. It is a mathematical one. It represents the critical radius around a black hole where the escape velocity, the speed needed to escape the black hole's gravitational pull, exceeds the speed of light. This is the key reason why not even light can escape. The very nature of spacetime is warped in such a way that once something passes the event horizon, it is effectively trapped. Now let's break this down. When you approach a black hole, things seem normal at first. Light travels in its usual way, and time flows at a regular pace. But as you get closer, things start to change. The gravitational pull increases as you approach the event horizon, and this causes time to behave strangely. The closer you get to the event horizon, the slower time seems to pass relative to an observer far away. This is known as gravitational time dilation. To an observer watching from a distance, it would appear as if an object approaching the event horizon would slow down and never quite reach it. However, for the object falling into the black hole, time continues to flow normally, and it crosses the event horizon without any noticeable change. Once the event horizon is crossed, nothing, absolutely nothing, can escape. Not matter, not radiation, not even information. The escape velocity inside the event horizon is greater than the speed of light, meaning that even light itself is unable to break free. This is why black holes are called black, because they don't emit light or any form of radiation that we can detect from the outside. The black hole becomes a dark, invisible region of space, with everything that crosses its event horizon disappearing from the observable universe. But what happens inside the event horizon? This is where things get even more mysterious. As you cross the event horizon, you would experience an overwhelming increase in gravitational forces. These forces are so intense that they can stretch and compress objects in what is known as spaghettification. Imagine a star or a spaceship falling toward a black hole. As the object gets closer, the difference in gravitational pull between the part of the object nearest to the black hole and the part farthest away becomes more and more extreme. The result is that the object would be stretched vertically, while simultaneously being compressed horizontally, like a piece of spaghetti being pulled apart. This extreme tidal force grows stronger as you get closer to the singularity, the black hole's center. Once you pass the event horizon, there is no way out. Any information that passes through the event horizon is lost to the outside universe. This has led to what is known as the information paradox. According to quantum mechanics, information about the state of particles should never be destroyed. But if the information about objects that fall into a black hole is lost beyond the event horizon, it presents a conflict with the fundamental principles of physics. This paradox has yet to be fully resolved, and scientists continue to debate the fate of information that crosses the event horizon. At the very center of a black hole lies the singularity, a point where gravity is so intense that space and time become infinitely distorted. The singularity represents a breakdown of the laws of physics as we understand them. At this point, the equations that describe spacetime, like Einstein's general theory of relativity, no longer hold true. The density becomes infinite, and the curvature of spacetime becomes infinite. Essentially, all known laws of physics break down in the singularity. One of the most compelling aspects of black holes is that, despite being surrounded by the event horizon, their effects can still be felt across great distances. For example, as matter is pulled toward the event horizon, it heats up and emits X-rays and gamma rays in the process. These emissions can be detected by astronomers far away, providing valuable information about the black hole and its surroundings. In fact, studying these emissions is one of the ways scientists observe and learn about black holes, even though the objects themselves are invisible. The event horizon and its associated phenomena are not just theoretical constructs. They have real, observable effects on the universe. For instance, the formation and growth of supermassive black holes at the centers of galaxies have a profound influence on the galaxies themselves. The immense gravity of these black holes can affect the motion of stars and the gas surrounding them, influencing the evolution of galaxies over billions of years. In some cases, supermassive black holes can even trigger the formation of new stars by compressing gas and dust in the surrounding galaxy. But despite the advancements in our understanding of black holes, the ultimate fate of anything that crosses the event horizon remains one of the greatest mysteries of modern physics. While it is clear that the object will be pulled toward the singularity, what happens to it once it reaches that point? Does it get crushed into a point of infinite density, or does it undergo some other transformation? Is it destroyed, or is there a way for it to re-enter another part of the universe? These questions remain unanswered, and until scientists develop a unified theory of quantum gravity that combines general relativity and quantum mechanics, the true nature of black holes will remain elusive. In essence, the event horizon is not just a boundary. It is the threshold between what we can observe and what lies beyond the limits of human knowledge. It represents the ultimate mystery of the cosmos, where our current understanding of space, time, and matter breaks down completely. Every black hole, with its event horizon, is a cosmic enigma, an invitation to explore the unknown and push the boundaries of what is possible to understand. As we continue to study these extraordinary objects, we move closer to unlocking the secrets hidden within their depths. The event horizon marks the limit of our observation, but it also marks the beginning of a new frontier, where the fundamental laws of physics are stretched to their breaking point, and the mysteries of the universe are waiting to be discovered. Time and space around black holes. The fascinating nature of black holes doesn't just lie in their ability to swallow everything in their vicinity, but also in the bizarre effects they have on the fabric of space and time itself. One of the most mind-boggling consequences of approaching a black hole is time dilation. As an object moves closer to the event horizon, the point of no return, the very nature of time begins to change. To understand this, we must delve into the concept of gravitational time dilation. Gravitational time dilation occurs because of the intense gravity near a black hole. As you get closer to the event horizon, the gravitational pull increases dramatically, and this causes time to slow down relative to an observer farther away. Imagine this scenario. If you were to fall toward a black hole, you would experience time moving normally from your own perspective. But to an observer far away from the black hole, it would appear as if you were moving in slow motion. The closer you get to the event horizon, the slower time appears to move. It's as though time is being stretched and warped by the immense gravitational forces. The difference is stark. If you fell toward the event horizon, you would witness seconds, minutes, and hours ticking away normally. But to someone watching from a distance, those same moments would appear to drag on for eternity. At the exact moment you reach the event horizon, from an outside perspective, it would seem as though you never quite cross it. Instead, you would freeze in time, suspended at the boundary, forever trapped in a moment that never truly passes. But time dilation is not just a theoretical concept. It has been observed on smaller scales around other massive objects. For example, satellites orbiting Earth experience a slightly different passage of time compared to clocks on the surface, due to Earth's gravity. This effect is real and measurable, though it is minuscule compared to the extreme time dilation that occurs near a black hole. This stretching of time has profound implications. It suggests that as objects approach the event horizon, they are caught in an irreversible process, with time itself bending to the gravitational will of the black hole. The closer an object gets to the event horizon, the more extreme these effects become. In theory, once you pass the event horizon, time itself could stop altogether. But we can't be sure because no one has ever crossed that line. What happens beyond this boundary remains one of the greatest mysteries in modern physics. Now, as we cross the event horizon, we are faced with the ultimate unknown. What happens inside the black hole? The truth is, we don't fully know. Once anything crosses the event horizon, it is lost to the observable universe, and no information can escape. We can only theorize what happens next. According to general relativity, the gravitational forces inside a black hole grow infinitely stronger as you approach the singularity, the very center of the black hole. The singularity is where mass is compressed into a point of infinite density, and space and time themselves collapse under the influence of this intense gravity. At this point, the equations of general relativity break down. Our current understanding of physics cannot explain what happens inside a black hole because we lack a theory of quantum gravity, a theory that combines the two pillars of modern physics: general relativity, which governs the large-scale structure of spacetime, and quantum mechanics, which governs the behavior of particles at the smallest scales. The singularity represents the breakdown of these theories, leaving us with a place where the known laws of physics no longer apply. Several theories attempt to describe what could happen inside a black hole. One of the most intriguing ideas is that when you cross the event horizon, you might be transported to another region of spacetime, perhaps even to another universe. This is known as the wormhole theory. In this scenario, the black hole would not be a cosmic graveyard, but a bridge to a distant part of the universe, or perhaps even to a completely different universe altogether. However, this idea remains speculative, as we currently have no direct evidence to support it. Another theory suggests that the intense gravity inside a black hole could rip apart anything that ventures too close. Known as spaghettification, this process occurs when the difference in gravitational pull between an object's near and far sides becomes so large that the object is stretched like spaghetti. It's a violent process, and anything that crosses the event horizon could be torn apart before it even reaches the singularity. This stretching and compression would make the object unrecognizable, reduced to a stream of particles. Yet, despite these dramatic theories, we cannot observe what truly happens inside a black hole. Once an object passes the event horizon, it is forever out of reach. This means that no matter how advanced our technology becomes, we will never be able to directly observe the interior of a black hole. What we know is limited to the effects black holes have on the surrounding space and how they interact with nearby objects. The true nature of the interior of a black hole remains hidden from us, locked away in a region where even light cannot escape. In essence, the event horizon represents the ultimate boundary of knowledge. It is a place where spacetime itself becomes so warped that our current understanding of the universe is rendered useless. Once something crosses that boundary, it is lost to the cosmos, leaving only the ripples of its passing. These ripples, in the form of gravitational waves, have been detected by instruments like LIGO, providing us with indirect evidence of black hole mergers. But when it comes to the secrets hidden behind the event horizon, we are left with more questions than answers. The study of black holes and their event horizons will continue to push the limits of science. As we develop new technologies and continue to study the cosmos, we may one day gain insights into what truly happens beyond the event horizon. Until then, black holes remain one of the greatest mysteries of the universe, a symbol of both the power and the limitations of human understanding. The cosmic abyss, as represented by the event horizon, invites us to explore the unknown, challenging us to reach the limits of what we can learn about the universe. Chapter 3. Our Solar System, a close-up on our cosmic neighborhood. The Sun, the heart of our solar system. The Sun, our closest star, is the heart and engine of our solar system. Without it, life on Earth would be impossible, and the very structure of our solar system would crumble. It contains 99% of the total mass in the solar system, which means that almost everything in our cosmic neighborhood, from the smallest asteroid to the largest gas giant, exists under the immense gravitational grip of this one powerful star. The Sun's massive size allows it to dominate the solar system with its gravity. Every planet, moon, asteroid, and comet in our system orbits the Sun, held in place by its pull. This gravitational influence extends far beyond the planets we see with the naked eye, reaching into the distant reaches of our solar system. Even the Oort cloud, a vast, icy region that marks the farthest boundary of the Sun's influence, is held in place by this incredible force. The Sun, in essence, is the gravitational anchor that keeps our solar system together. Let's pause to think about the Sun's overwhelming size. It has a mass that is approximately 330,000 times that of Earth. To put that in perspective, the Sun is so massive that it could fit about 1.3 million Earths inside it. The sheer size is mind-boggling, and yet it's only one of hundreds of billions of stars in the Milky Way. The Sun's size and mass are what enable it to exert such a profound influence on everything around it. Without the Sun's gravitational pull, the planets would drift aimlessly through space, no longer bound to the solar system, and Earth would cease to exist as we know it. But gravity is not the only force the sun exerts. The sun also emits a continuous stream of charged particles, known as the solar wind, that flows outward from the sun in all directions. This solar wind creates a bubble of charged particles around the solar system, known as the heliosphere. The heliosphere extends far beyond the orbit of Pluto, protecting the planets from the harsh radiation and cosmic rays that fill interstellar space. The heliosphere acts as a shield, allowing life on Earth to thrive and protecting our planet from the damaging effects of space radiation. The sun's gravitational pull also plays a key role in shaping the orbits of the planets. Each planet in our solar system moves in an elliptical orbit around the sun, with the sun at one focus of the ellipse. The force of gravity from the sun keeps the planets in their orbits, preventing them from drifting off into space. The sun's gravity is so powerful that it affects even the paths of comets and asteroids, pulling them into predictable orbits that bring them into the inner solar system before they are flung back out into the distant reaches of space. This gravitational dominance extends to the sun's relationship with the planet's moons. Earth's moon, for example, is locked in a stable orbit around our planet, thanks to the gravitational pull of both Earth and the sun. The sun's gravitational influence is responsible for the fact that the moon doesn't simply drift away into space, but instead continues to orbit Earth, contributing to the stability of our planet's rotation and the tides that shape life on Earth. As powerful as the sun's gravity is, it also plays a central role in maintaining the balance of the solar system. The interactions between the sun's gravity and the planet's movements create a delicate equilibrium, ensuring that the solar system remains a stable, predictable system. It is this balance of forces that has allowed life on Earth to evolve and thrive over billions of years. While the sun is the dominant force in our solar system, it is also an ever-changing, dynamic entity. Its energy output fluctuates over time, and its magnetic field is constantly shifting. These changes, though subtle on human timescales, can have profound effects on the solar system as a whole. The sun's magnetic activity, for example, is responsible for the solar cycle, an 11-year period of increasing and decreasing solar activity that affects everything from solar flares to the auroras we see in Earth's polar regions. These fluctuations in solar activity can also impact Earth's climate, and, in extreme cases, solar storms can power grids and even pose risks to astronauts in space. Despite its size and importance, the sun is just one of many stars in the Milky Way. However, its gravitational influence on our solar system is unparalleled. The sun holds everything in its grasp, from the smallest particles of dust in the asteroid belt to the largest planets, such as Jupiter and Saturn. This gravitational force is the invisible thread that connects everything in our solar system, making the sun the central anchor of our cosmic neighborhood. The sun's vitality also lies in its role as the source of life-giving energy. Its energy drives the weather patterns on Earth, powers photosynthesis in plants, and provides warmth and light to sustain life. Without the sun's constant energy, our planet would be a frozen, lifeless rock, drifting aimlessly in space. The sun's role in sustaining life on Earth cannot be overstated. It is the most important force in our solar system, the reason our planet is habitable, and the reason the Earth exists as a vibrant, thriving world. However, the sun is not a stable, static force. Over time, it will continue to evolve. As the sun reaches the end of its life, it will exhaust the fuel in its core, eventually leading to dramatic changes. But for now, the sun remains the central force of our solar system, and its gravitational grip ensures that everything in the solar system continues to orbit in harmony. The sun's constant presence, its size, and its forceful gravity are what keep the solar system alive and functioning, making it an indispensable part of the story of our universe. In the next chapter, we'll explore the planets that orbit around the sun, each with its own unique characteristics and mysteries. From the scorching surface of Mercury to the icy expanse of Neptune, we'll look at how the sun's gravitational pull influences each world and the conditions that make our solar system a truly remarkable place in the vast cosmos. The process of nuclear fusion within the sun and its long-term life cycle. The sun is not just a glowing orb in the sky. It is a massive ball of energy, a star that powers our solar system and drives life on Earth. At the core of the sun, an incredibly complex process is constantly taking place. Nuclear fusion. This process is what gives the sun its immense energy, and understanding how it works allows us to grasp the very life cycle of our star. Nuclear fusion occurs when the sun's immense gravity causes hydrogen atoms in its core to collide with such force that they fuse together, creating helium and releasing an enormous amount of energy. This energy is released in the form of light and heat, radiating outward to the surface of the sun, where it eventually escapes into space. The energy produced by this fusion is what powers the sun and sustains its brightness and heat. Without this process, the sun would have no light or warmth, and life on Earth would be impossible. The sun has been undergoing nuclear fusion for about 4.6 billion years, and it's expected to continue for several billion more. The energy produced by fusion pushes outward, balancing the inward pull of gravity. This delicate balance has kept the sun stable for much of its life. For now, the sun is in what is known as the main sequence phase of its life cycle. During this time, it primarily fuses hydrogen into helium in its core, producing vast amounts of energy that sustain the solar system's temperature and weather patterns. As the sun continues to burn through its hydrogen fuel, however, this process will eventually change. The sun has only a finite supply of hydrogen in its core, and as it gets depleted, the core will contract under gravity, causing the temperature to rise. This will trigger a new phase in the sun's life, the red giant phase. When the sun becomes a red giant, its core will become hotter and denser, while its outer layers will expand. The outer layers of the sun will puff up, and the sun's diameter will increase dramatically, possibly swallowing the inner planets, including Mercury, Venus, and even Earth. As the sun's outer layers expand, they will cool, giving the sun a reddish hue, hence the term red giant. During this phase, the sun will begin to fuse heavier elements like helium into carbon and oxygen, a process that produces even more energy. The red giant phase will not last long in the grand scheme of the sun's life. Eventually, the sun will shed its outer layers, creating a shell of gas and dust known as a planetary nebula. The core of the sun will continue to shrink, becoming increasingly dense and hot. Without the outward pressure of fusion in the outer layers, the core will collapse under its own gravity, reaching a point where nuclear fusion can no longer take place. At this point, the sun will transform into a white dwarf. A white dwarf is the dense, hot remnant of a star that has exhausted its fuel. Unlike larger stars, which explode in a supernova when they die, the sun will not go out with a violent bang. Instead, it will quietly shed its outer layers and leave behind a small, incredibly dense core. This core, now a white dwarf, will be composed mostly of carbon and oxygen. Though it will still be incredibly hot initially, it will no longer undergo fusion and will gradually cool over billions of years. The transformation from a red giant to a white dwarf marks the end of the sun's active life cycle. However, this is not the final end. Over the course of many billions of years, the white dwarf will continue to cool, eventually fading into the cold, dark expanse of space. It will no longer emit any light or heat, and it will remain as a faint, dead remnant of what was once a powerful star. Despite this eventual fade to darkness, the sun's impact on our solar system is immeasurable. It has provided the heat, light, and energy necessary for life on Earth. Its gravitational pull has shaped the orbits of the planets, keeping them locked in their paths around the solar system. As the sun undergoes its transformation, it will leave behind a changed solar system, perhaps barren and lifeless, but still a testament to the energy and life it once supported. The process of nuclear fusion within the sun and its long-term life cycle reveal not only the immense power of stars, but also the inevitability of change in the cosmos. Every star, including our sun, is born, lives, and eventually dies, transforming in ways we can only begin to understand. The sun's future as a red giant and then a white dwarf is inevitable, a natural progression dictated by the laws of physics and the limits of its hydrogen fuel. It serves as a reminder of the impermanence of the universe and the cycles of birth, death, and rebirth that shape the very fabric of space and time. As we explore the wonders of our solar system, the sun's role will remain central. It is the source of life, the engine of our solar system, and the star that will ultimately shape its own fate and that of the planets that orbit it. In the coming chapters, we will journey through the planets that depend on the sun's light, each one a unique world shaped by its proximity to this powerful star. Planets and their peculiarities.
Venue.
As we continue to explore the wonders of our solar system, we turn our focus to one of the most enigmatic and intriguing planets.
Venue.
This second planet from the Sun, often called Earth's sister planet due to its similar size and composition, harbors strange and extreme conditions that set it apart from any other world we know. Venus is unique in many ways, but perhaps the most mind-boggling fact about this planet is that a single day on Venus lasts longer than an entire year. This means that Venus takes longer to rotate once on its axis than it does to orbit the Sun. While Earth completes one rotation in 24 hours, Venus takes about 243 Earth days to complete one rotation. In contrast, Venus only takes about 225 Earth days to orbit the Sun. This curious phenomenon means that a day on Venus is longer than a year on Venus, making its rotation one of the slowest in the entire solar system. Now, why does Venus rotate so slowly and in the opposite direction to most of the other planets? The planet rotates in what is called retrograde motion, meaning it spins in the opposite direction to most planets, including Earth. On Venus, the Sun would rise in the west and set in the east, the exact opposite of what we experience on Earth. This backward spin is thought to be the result of a massive collision with another celestial body early in the planet's history, which may have caused it to spin in the opposite direction. Venus' retrograde rotation is not just an interesting quirk. It has profound implications for the planet's atmosphere. The extreme rotation rate and the fact that Venus has such a thick atmosphere contribute to the planet's incredibly hot surface temperatures. The thick atmosphere, composed primarily of carbon dioxide with clouds of sulfuric acid, creates a runaway greenhouse effect. This means that heat from the Sun is trapped, and temperatures on Venus soar to an average of around 467 degrees Celsius, 872 degrees Fahrenheit. Hotter than the surface of Mercury, the closest planet to the Sun. These extreme temperatures make Venus an inhospitable world. The thick clouds that envelop the planet reflect most of the sunlight, making it difficult to study the surface with visible light. However, radar technology has allowed us to map the surface, revealing a world of volcanoes, vast plains, and mountain ranges. The thick atmosphere also exerts crushing pressure, about 92 times the pressure we experience at sea level on Earth. This pressure is enough to crush spacecraft that have dared to land on Venus. But even these fleeting visits have provided crucial insights into the planet's hostile environment. The thick atmosphere of Venus also causes powerful winds, which, combined with the planet's slow rotation, creates one of the most fascinating weather systems in the solar system. Venus experiences what is known as superrotation, where the atmosphere circulates much faster than the planet itself rotates. Winds on Venus can reach speeds of up to 400 kilometers per hour, about 250 miles per hour, circulating around the planet at speeds far faster than the planet's slow rotation. This creates an almost unrelenting atmospheric flow, constantly shifting the clouds and weather patterns on the planet's surface. The fact that Venus has such a slow and retrograde rotation, combined with its extreme temperatures and thick, toxic atmosphere, makes it one of the most extreme environments in the solar system. While it may be similar to Earth in size and composition, its surface conditions are radically different, making Venus a world of extreme heat, pressure, and weather. These conditions, however, also make Venus a fascinating subject of study. Scientists are still trying to fully understand how Venus' atmosphere works, what caused its extreme temperatures, and whether it might have ever had the potential to support life in the distant past. Some theories suggest that Venus may have had oceans billions of years ago, but the planet's extreme greenhouse effect over time likely caused those oceans to evaporate, leaving behind the scorching, inhospitable surface we see today. What we do know for certain is that Venus is a world unlike any other in our solar system. Its day is longer than its year, its rotation is in the opposite direction to most other planets, and its atmosphere is a deadly, crushing environment. Yet despite these extreme conditions, Venus remains a key part of our understanding of planetary science, offering clues about the early evolution of planets and the processes that shape planetary atmospheres. As we continue to explore the solar system, Venus will remain a planet that challenges our assumptions and forces us to rethink what we know about the nature of planets. It's a world where time seems to slow down, where heat and pressure are extreme, and where the forces of nature are at their most intense. In the grand scale of the cosmos, Venus may be just one planet, but its strange, extreme nature provides valuable insights into the workings of the universe. Mars, the fourth planet from the Sun, is often referred to as the red planet due to its distinctive rusty hue. But there is more to Mars than meets the eye. Beneath its reddish surface, a world of unique and fascinating phenomena awaits discovery. Mars is not only a world of scientific interest for its potential to host life in the past or future, but it also harbors a surprising natural spectacle, blue sunsets. While we on Earth are accustomed to seeing sunsets bathed in warm reds, oranges, and yellows, the sunsets on Mars are eerily different. The dust in Mars' thin atmosphere plays a crucial role in creating a stunningly beautiful and strange visual effect. As sunlight passes through the Martian atmosphere, the fine dust particles in the air scatter the sunlight. On Earth, the shorter wavelengths of light, like blue and violet, are scattered out of sight, giving us those familiar red and orange sunsets. However, on Mars, the fine dust in the atmosphere is much more efficient at scattering the shorter blue wavelengths, allowing blue light to filter through and dominate the evening skies. This results in a strikingly blue sunset, a rare and beautiful occurrence that only happens on Mars. The dust in Mars' atmosphere isn't just responsible for its blue sunsets. It also influences many other aspects of the planet's climate and weather. Mars' atmosphere is composed primarily of carbon dioxide, with only trace amounts of water vapor and nitrogen. It's incredibly thin, about 100 times thinner than Earth's atmosphere, which contributes to the planet's frigid surface temperatures. The dust particles, made of iron oxide and other minerals, are so fine that they can be carried high into the air, where they form massive dust storms. These storms can cover the entire planet, affecting the temperature and weather patterns on Mars. The dust storms on Mars are so intense that they can block out the sun, creating an eerie, sepia-toned sky that envelopes the planet for days or even weeks. But these dust storms are not the only mysterious aspects of Mars' weather. The planet is known for having extreme temperature variations. During the day, the temperature can rise above freezing, but at night, it can plummet to a bone-chilling -125 degrees Celsius, -195 degrees Fahrenheit. This drastic shift in temperature is due to the thin atmosphere, which cannot retain heat like Earth's thicker atmosphere. Without clouds to trap the warmth from the sun, the heat escapes into space rapidly, leading to extreme temperature swings. Despite these harsh conditions, Mars has long been a subject of fascination for scientists, as it is the most Earth-like planet in our solar system. The presence of ice at its poles, evidence of ancient riverbeds, and the discovery of minerals that form in liquid water all suggest that Mars may have had a much warmer and wetter climate in the distant past. This has led scientists to speculate that Mars might have once supported microbial life, and there is still the possibility that life, in some form, could exist beneath its surface today. The discovery of methane in the atmosphere, a gas often associated with biological activity, adds another layer of intrigue to Mars' mysteries. Mars' atmosphere, while thin and inhospitable by Earth's standards, offers glimpses into the planet's complex history. Its blue sunsets, driven by dust scattering, are just one of the many unusual features that make Mars such an interesting world to study. As scientists continue to explore Mars, both with rovers and orbiters, we are slowly uncovering the planet's secrets. Secrets that may hold the key to understanding whether life once existed there or might still exist in the underground depths. This world of contrasts, its red surface, blue sunsets, dust storms, and harsh conditions, forms a compelling backdrop to our quest for knowledge about Mars. It challenges our understanding of what makes a planet habitable and forces us to reconsider our place in the universe. Whether Mars once hosted life or remains a barren world is still unknown, but what we do know is that it is a planet of extraordinary beauty and intrigue, a place that continues to capture our imaginations and push the boundaries of science. As we venture forward, we'll examine the rest of the solar system's unique worlds, each offering its own set of wonders and challenges. But Mars, with its blue sunsets and enigmatic history, will always remain a focal point in the search for answers about life beyond Earth. Jupiter. Jupiter, the largest planet in our solar system, is a world of extremes. With a diameter of over 139,000 kilometers, it is more than 11 times the size of Earth. It has a mass that is 318 times greater than ours, and its volume could hold more than 1,300 Earths. But despite its colossal size, what truly sets Jupiter apart from other planets is its ever-stormy atmosphere, particularly the Great Red Spot. The Great Red Spot is a massive, persistent storm that has been raging on Jupiter for at least 400 years. This storm is so large that it could swallow Earth whole. It has a reddish hue, which has baffled scientists for centuries. The storm is located in Jupiter's southern hemisphere and measures about 16,000 kilometers in width, roughly 1.5 times the diameter of Earth. The swirling clouds of this storm move at speeds of up to 432 kilometers per hour, about 268 miles per hour, which is faster than any hurricane we experience on Earth. For centuries, the Great Red Spot has been a defining feature of Jupiter. It has been observed since at least the 1600s, when the first telescopic observations were made by astronomers like Galileo. But in recent decades, something unusual has been happening. The Great Red Spot has been shrinking. This storm, which once spanned as much as 40,000 kilometers across, has been steadily decreasing in size. In fact, over the past few decades, it has shrunk by about 20% in both width and height. What is causing this dramatic change? That remains a mystery. Scientists have several theories about the shrinking of the Great Red Spot. One possibility is that changes in Jupiter's atmospheric dynamics, such as alterations in wind patterns or the temperature of the surrounding clouds, are affecting the storm's longevity. Some believe that as Jupiter's atmosphere is subjected to changes in solar radiation and heat distribution, the storm's size and intensity naturally fluctuate. But no one knows for certain why the storm is shrinking, or if it will eventually disappear entirely. The mystery surrounding the Great Red Spot extends beyond its size. The nature of the storm itself is enigmatic. Why does it have that distinct red color? Some scientists suggest that it is the result of complex chemical reactions in Jupiter's upper atmosphere, where gases like ammonia and methane interact with ultraviolet radiation from the sun. These reactions may produce the reddish compounds that give the storm its striking appearance. However, the exact chemical composition of the storm's red hue remains unknown. Adding to the intrigue, the Great Red Spot is not a single, simple storm. It is composed of numerous swirling eddies and bands, some of which rotate in opposite directions. This gives the storm its complex structure, where different atmospheric forces interact with one another in an ongoing dance. This interaction is why the Great Red Spot has persisted for so long, and why it continues to be a powerful feature of Jupiter's atmosphere. Even with the shrinking of its size, the storm remains a massive and influential force, maintaining its place as 1-0. The Great Red Spot is not the only storm in Jupiter's turbulent atmosphere. Jupiter is home to numerous other massive storms, including the turbulent bands of clouds that encircle the planet in alternating light and dark bands. These bands, known as zones and belts, are made up of different gases, such as ammonia and methane, and are driven by high-speed winds that can reach speeds of 600 kilometers per hour, about 373 miles per hour. These winds are part of a larger circulation system that creates the planet's unique striped appearance. Unlike the Great Red Spot, these storms are much smaller in scale, but they still represent the immense energy and power of Jupiter's atmosphere. In addition to the Great Red Spot and the bands of clouds, Jupiter's atmosphere is also home to intense lightning storms. These storms are the largest in the solar system, producing lightning bolts that are up to 1,000 times more powerful than those on Earth. These bolts of lightning are not only a sign of the planet's chaotic weather patterns, but also provide valuable insights into the composition of Jupiter's clouds and the processes that occur in its atmosphere. Despite the mysteries surrounding the Great Red Spot's shrinking and its overall behavior, one thing is clear: Jupiter's atmosphere is an incredibly dynamic and ever-changing environment. The planet's size and composition make it a powerful force in our solar system, and its weather patterns, storms, and atmospheric features continue to intrigue scientists. Jupiter's role in the solar system extends beyond its weather. However, as the largest planet in the system, it has a gravitational influence that affects the orbits of nearby planets and asteroids. Its immense gravity helps shape the structure of the solar system, pulling in comets and asteroids, some of which collide with Jupiter rather than with the inner planets. Jupiter's gravitational pull has also played a role in the formation of the asteroid belt, helping to keep it in place between Mars and Jupiter. The shrinking of the Great Red Spot, along with the other fascinating aspects of Jupiter's atmosphere, offers us a glimpse into the complex and ever-evolving nature of our solar system. As we continue to study Jupiter and its many mysteries, we uncover more about the planet's history and the forces that shape its weather, its storms, and its future. Jupiter is a reminder of the unpredictable and powerful forces at work in the cosmos, and it serves as a testament to the extraordinary phenomena that exist just beyond our planet. Saturn, the sixth planet from the Sun, is one of the most visually stunning worlds in our solar system. Its majestic rings make it instantly recognizable, and they have fascinated scientists and stargazers alike for centuries. Saturn's rings are made of countless ice and rock particles, varying in size from tiny grains of sand to massive chunks as large as mountains. These rings surround the planet in a wide, flat disk, creating one of the most iconic and beautiful sights in the cosmos. What is truly remarkable about Saturn's rings is their sheer size. They stretch out over 280,000 kilometers from the planet's surface, yet they are incredibly thin. In fact, some sections of the rings are only about 10 meters thick. This means that despite their vast width, the rings are surprisingly shallow. If you were to fly through Saturn's rings, you would be able to pass through them in mere minutes. The fact that these rings are so thin in relation to their enormous diameter is a curious feature that has intrigued astronomers for decades. The composition of Saturn's rings is also fascinating. While much of the material is made of water ice, the rings also contain smaller amounts of rock, dust, and other debris. The ice particles range from tiny flecks of snow to massive chunks the size of buildings. These particles are constantly colliding and interacting with each other, creating a dynamic, ever-changing environment. Some of the larger particles in the rings can even create gaps or divisions, known as ring divisions, by gravitationally pulling other material out of their path. One of the most famous features of Saturn's rings is the Cassini division, a dark gap in the rings that separates the A and B rings. This division is caused by the gravitational influence of Saturn's moon, Mimas, which has caused the particles in the gap to clear out, creating a void between the two rings. The presence of these gaps and divisions is a testament to the dynamic and active nature of the rings. Saturn's rings are not a static, frozen structure, but a constantly evolving system shaped by the forces of gravity, collisions, and the interactions between particles. The formation of Saturn's rings remains a topic of debate among scientists. Some believe that the rings formed billions of years ago, possibly from the remnants of a moon that was shattered by a collision with another object. Others suggest that the rings could be much younger, having formed from the debris left over from a comet or asteroid that was torn apart by Saturn's powerful gravity. There is even the possibility that the rings could be temporary, with the material eventually being pulled into the planet or scattered into space over time. Despite the uncertainty about their origin, Saturn's rings provide valuable insight into the processes that shape planetary systems. The rings are thought to be a result of the gravitational forces at work within Saturn's system, with the planet's moons playing a crucial role in shaping the structure of the rings. Some moons, like Pan, act as shepherd moons, preventing material from spreading too far by keeping it confined to specific regions. Other moons, like Enceladus, are thought to contribute material to the rings by releasing icy particles through geysers on their surfaces. The rings are also a key feature of Saturn's interaction with its moons. While the rings themselves are composed mostly of ice and rock, the gravitational pull of Saturn's moons affects the behavior of the particles within the rings. The moons create waves and ripples in the rings, causing the ice and rock particles to move and shift in response. These gravitational interactions create a dynamic, constantly changing environment, where particles move in and out of the rings, creating patterns and structures that are continually evolving. The complexity of Saturn's rings is matched by the beauty and mystery they present. The fact that these rings are so thin, yet so wide, creates a paradox that continues to challenge our understanding of planetary ring systems. They are a perfect example of the intricate balance of forces that govern the universe, where gravity, motion, and matter interact in ways that we are still trying to fully understand. As we continue to explore Saturn and its rings, we are continually learning more about the forces that shape our solar system. The study of Saturn's rings not only gives us a deeper understanding of the planet itself, but also provides valuable clues about the formation and evolution of planetary systems as a whole. From the icy particles that make up the rings to the moons that interact with them, Saturn's rings are a dynamic, ever-evolving system that continues to reveal new mysteries about the cosmos. While Saturn's rings may appear to be a beautiful and serene feature of the planet, they are anything but simple. They are the product of a complex interplay of forces, interactions, and collisions, creating a constantly shifting and evolving system. Saturn's rings are a perfect example of the dynamic nature of the universe, where beauty and mystery coexist, and where the forces of nature continue to shape the cosmos in ways that we are only beginning to understand. The rings of Saturn remain one of the most awe-inspiring features in our solar system, not only for their stunning appearance but for the many mysteries they hold. As we explore the nature of Saturn's rings, we begin to understand more about the forces that shape the universe and the dynamic processes that govern the planets, moons, and other celestial bodies. With every discovery, Saturn's rings continue to captivate our imaginations and inspire our curiosity, reminding us of the vast, ever-changing nature of the universe around us. Other wonders of our solar system: the moon's slow drift. The moon, Earth's faithful companion, has been with us for as long as our planet has existed. For billions of years, it has orbited Earth, stabilizing our planet's rotation and influencing life in ways we can hardly comprehend. But there is a fascinating, slow, and quiet transformation happening between Earth and its moon, one that unfolds over an immense timescale. The moon is slowly drifting away from Earth, moving at a rate of about 3.8 centimeters per year. While this may seem like an insignificant amount in the short term, over the course of millions and billions of years, this gradual drift will have profound consequences on both the moon and Earth. This slow movement is the result of tidal interactions between the two bodies. The gravitational forces between Earth and the moon are in constant flux, creating tidal bulges on Earth's surface. These tidal bulges are the result of the moon's gravity pulling on Earth's oceans, causing them to bulge out toward the moon. At the same time, Earth's gravity pulls on the moon, exerting a force that creates tidal bulges on the lunar surface as well. This tidal interaction is not only responsible for the rise and fall of the tides on Earth, but also for the slow recession of the moon. As Earth's oceans are pulled toward the moon, they exert a backward pull on the planet's rotation. This interaction causes Earth's rotation to gradually slow down, and in return, the moon is pushed into a higher orbit, moving away from Earth at that rate of 3.8 centimeters per year. At first glance, this might seem like a slow, almost imperceptible shift in the relationship between Earth and its moon. However, over millions of years, this movement becomes significant. In fact, when the moon first formed, it was much closer to Earth, perhaps just 20,000 kilometers away, compared to the current distance of around 384,400 kilometers. In the distant past, the moon was much larger in the sky, and its gravitational influence on Earth was far stronger, leading to more extreme tidal effects. This gradual retreat of the moon will continue for billions of years, and it will eventually alter the way Earth and the moon interact. As the moon moves farther from Earth, the rate of Earth's rotation will continue to slow down, though at an ever-decreasing pace. Over billions of years, Earth will experience longer and longer days as the moon's gravitational pull weakens, reducing its ability to slow Earth's rotation. But Earth's slowing rotation will also continue to push the moon farther away. One day, in about 5 billion years, when the moon has drifted far enough away, Earth's rotation will slow to the point where a day on Earth will be as long as a month, and the moon will appear much smaller in the sky. However, before this dramatic change occurs, there will be other consequences. For instance, the moon's gravitational pull is responsible for stabilizing Earth's axial tilt, which in turn stabilizes our planet's climate. Without the moon's influence, Earth's axial tilt would wobble more significantly, leading to greater variations in our planet's climate over time. This could have a profound impact on the conditions that support life on Earth, as drastic shifts in climate could lead to unstable environments. Interestingly, the moon's slow drift away from Earth will not go on forever. As the moon moves farther from Earth, the tidal interactions will gradually weaken. Eventually, the moon will reach a point where it will no longer have enough gravitational pull to continue pulling on Earth's oceans and slowing its rotation. At that point, Earth's rotation will stabilize, and the moon will remain in its orbit, no longer drifting away. However, before this occurs, the effects of the moon's retreat and the slowing of Earth's rotation will have long-lasting consequences on the dynamics of our planet's systems. Although the process of the moon moving away from Earth is gradual, its implications are vast. The moon's influence on Earth, particularly its effects on our rotation, tides, and climate, has been essential to the development of life as we know it. The slow, quiet dance between Earth and its moon continues, and even as the moon drifts away, it will leave behind a legacy that has shaped, and will continue to shape, the conditions for life on Earth. As we reflect on the moon's gradual retreat, we gain insight into the broader dynamics of our solar system and the slow but inevitable changes that occur within it. The moon's drift is a testament to the forces of gravity at play, and its steady departure reminds us of the ever-changing nature of the universe. Over the course of time, our planet and its lunar companion will continue to evolve, changing in ways that we are only beginning to understand. The moon's influence, though gradually fading, will remain a central part of the story of Earth, shaping our world in ways both subtle and profound for billions of years to come. Cold welding. In the vacuum of space, where conditions are vastly different from what we experience on Earth, strange and fascinating phenomena occur. One of these curious occurrences is known as cold welding. This process, which happens only in the extreme environment of space, involves two pieces of the same metal fusing together without any external heat or pressure. The metal pieces effectively weld themselves together, a phenomenon that would be impossible in the familiar environment on Earth, where heat and pressure are required for welding. Cold welding occurs because of the unique properties of the vacuum of space. On Earth, when metals are brought together, the atoms on their surfaces have a thin layer of oxide or other contaminants that prevent them from directly bonding. However, in the vacuum of space, there is no atmosphere to cause oxidation or contamination. This allows the metal atoms on the surfaces of two pieces of the same metal to come into direct contact. In space, the absence of air means that the usual barriers to bonding are gone. As a result, when two metal surfaces are brought together, the atoms on the surfaces align perfectly, and the pieces bond together as if they were a single piece of metal. This process is often described as cold welding because it occurs without the need for the high temperatures associated with conventional welding. In the extreme cold of space, where temperatures can drop to hundreds of degrees below freezing, the concept of heat seems far removed. Yet, despite the frigid conditions, the absence of air and the lack of oxidizing agents enable the atoms to bond, making cold welding a purely atomic-level phenomenon. In space, this phenomenon can have important practical implications. Cold welding can occur naturally in the harsh conditions of space, but it can also present challenges in the design of spacecraft and satellites. If two metal parts come into direct contact in space, they might unintentionally fuse together, potentially leading to mechanical malfunctions. For instance, parts of a spacecraft could become stuck together, preventing components from moving or functioning properly. Engineers working on spacecraft design must take into account the possibility of cold welding and carefully choose materials and designs to prevent unwanted fusion of metal parts. In addition to its impact on spacecraft engineering, cold welding also plays a role in the formation of cosmic structures. In the vastness of space, where small particles of metal and dust are common, cold welding can occur on a much larger scale. Tiny particles, such as those in asteroid belts, could fuse together over time, forming larger clumps of material. This process is a contributing factor to the gradual growth of asteroids and other small bodies in space, where small particles can stick together and gradually accumulate into larger masses. Interestingly, cold welding also presents opportunities in advanced materials science and manufacturing. Researchers have been studying cold welding for its potential applications in creating new materials and technologies. By understanding how metal atoms bond in the vacuum of space, scientists hope to develop new techniques for fabricating materials with unique properties. These materials could have applications in everything from space exploration to high-performance engineering on Earth. Despite its potential applications, cold welding remains a mysterious and somewhat elusive phenomenon. The exact conditions under which cold welding occurs and the factors that influence the process are still being studied by scientists. One of the key challenges in understanding cold welding is replicating the conditions of space in a laboratory setting. The vacuum of space, along with the extreme cold and lack of oxygen, creates an environment that is difficult to simulate on Earth. As a result, much of our knowledge about cold welding comes from observations of materials in space, rather than controlled experiments. What makes cold welding particularly intriguing is that it highlights the differences between the world we live in and the conditions of space. On Earth, heat, pressure, and environmental factors like oxygen play a significant role in shaping how materials behave. But in space, these forces are absent, and as a result, we encounter phenomena that challenge our understanding of physics and material science. Cold welding serves as a reminder that space is not a mere vacuum, but a dynamic environment where the rules we take for granted on Earth don't always apply. It's a place where materials behave in surprising ways, and where forces beyond our comprehension shape the very structure of the universe. By studying cold welding, we not only gain insight into the unique behavior of materials in space, but we also take another step toward unlocking the mysteries of the cosmos, where even the simplest phenomena can be complex and awe-inspiring. The study of cold welding is just one example of how space continues to challenge our understanding of the physical world. As we delve deeper into the mechanics of the universe, we uncover new forces, new behaviors, and new phenomena that push the limits of our knowledge. Space is a place of endless wonder, where the unexpected becomes reality, and where even the most curious occurrences, like cold welding, remind us that there is always more to learn, discover, and explore. Chapter 4: Space Oddities and Mysteries. Diamonds in Space. Beyond the familiar planets of our solar system, there exist far more extraordinary and unusual worlds that defy our expectations. One such planet, 55 Cancri E, has captured the imagination of astronomers and stargazers alike. Located about 40 light-years away in the constellation of Cancer, 55 Cancri E is a planet that is unlike anything we could ever have imagined. This world is believed to be largely composed of diamond, a discovery that has shifted our understanding of what types of planets can exist in the universe. 55 Cancri E orbits its parent star, a sun-like star, in just about 18 hours, making it incredibly close to its star. Its proximity to the star means that the planet is extremely hot, with surface temperatures soaring above 2,000 degrees Celsius, 3,632 degrees Fahrenheit. Such extreme temperatures would be inhospitable to life as we know it, but they create conditions that allow for a surprising phenomenon: the creation of diamond-like material deep within the planet's interior. This possibility of diamond formation is due to the high pressure and temperatures that exist on 55 Cancri E. Under these extreme conditions, carbon, a primary component of diamonds, could crystallize, forming diamonds deep within the planet. The planet is thought to be composed of a combination of rocky material, water, and carbon. But it's the high-pressure conditions that cause the carbon to bond into crystal structures, creating a world that is essentially one giant, shimmering diamond. It's as though the entire planet is a precious jewel suspended in the cosmos. The discovery of 55 Cancri e raises fascinating questions about the types of planets that can exist outside our solar system. For decades, scientists have studied exoplanets, planets that orbit stars other than our sun, but the discovery of a planet that might contain a vast amount of diamond material challenges the boundaries of our imagination. It suggests that there are forms of matter and worlds that we have not yet fully understood, opening up new possibilities for the kinds of planets we might one day find. How common are planets like 55 Cancri e in the universe? Can we find more diamond planets, or is 55 Cancri e a rare anomaly? The answer to these questions is still unclear, but the discovery has prompted scientists to consider new ways of studying exoplanets and their composition. As technology advances, astronomers may be able to better detect planets with similar characteristics. There are already other candidates in the search for diamond worlds, and as we continue to explore the vast reaches of space, we may come across even more planets with unique compositions and strange properties. The study of planets like 55 Cancri e also pushes us to rethink how planets form. Most planets form from gas and dust that surrounds a young star, a process known as accretion. As this material clumps together, it forms the core of the planet, while the surrounding material builds up to form the planet's atmosphere and surface. On 55 Cancri e, the high temperatures and pressure likely caused chemical reactions that turned the carbon present into diamonds, resulting in a planet that could very well be made of solid diamond on the inside. This discovery raises the intriguing question: could there be other planets in the universe made entirely or mostly of precious materials, such as diamonds, rubies, or sapphires? While we don't yet know the full extent of exoplanet compositions, the existence of 55 Cancri e suggests that the universe holds many more surprises, with planets and materials we can only begin to understand. These celestial bodies, made of such rare and valuable materials, challenge our concepts of what makes a planet habitable or valuable. In addition to its potential for diamond, 55 Cancri e offers a glimpse into the conditions of exoplanet atmospheres and planetary compositions. The heat and pressure present on this planet may also contribute to the formation of other exotic materials, such as silicates and metallic compounds, giving scientists a window into the planet's atmospheric conditions. These high-pressure environments offer a natural laboratory for studying materials under extreme conditions, giving researchers valuable data about how such planets might behave in the future. The discovery of 55 Cancri e and similar planets also speaks to the potential of space exploration. As our telescopes and detection methods improve, we may soon be able to identify planets with even more extreme and unusual properties. These discoveries open up new frontiers for space exploration and challenge our ideas about the variety of worlds that exist in the universe. The idea that a planet could be made of diamond is a reminder of how much we still have to learn about the cosmos and how much mystery remains just beyond our reach. In the search for exoplanets, scientists continue to discover new worlds that defy our expectations. Some are rocky, some are gaseous, some are frozen, and some, like 55 Cancri e, are a mix of all of these, yet formed in entirely different ways. The existence of diamond planets invites us to consider the possibilities of other planetary systems that are even more bizarre, strange, or valuable than we could have ever imagined. 55 Cancri e is a testament to the amazing diversity of the universe, and it reminds us that our solar system, with its familiar planets and moons, is just a small part of a much grander cosmic tapestry. The potential for discovery is limitless, and as we look deeper into space, we will continue to uncover more secrets about the strange, beautiful, and awe-inspiring worlds that exist far beyond the Earth. The silent cosmos, space, the final frontier, is a vast, silent expanse, a place where sound, as we know it, does not exist. You've likely heard the iconic phrase, "In space, no one can hear you scream," from science fiction. But this isn't just a dramatic tagline. It's the cold, hard truth. Sound, the way we perceive it, cannot travel through space. Sound is a vibration that travels through a medium, like air, water, or solid objects. These vibrations create waves that move through the medium, eventually reaching our ears and being interpreted as sound. On Earth, this process works because we have an atmosphere, a medium that allows these vibrations to travel. but space is a vacuum. A vacuum is an empty expanse that lacks matter, meaning there's nothing to carry those sound waves. Without molecules to vibrate and pass on the energy, sound simply cannot propagate. The silence of space, then, is absolute. This concept can be difficult to grasp since we are surrounded by sound in our everyday lives. On Earth, we are constantly bombarded by sounds. Voices, traffic, wind, the hum of machinery, music, all created by molecules vibrating and transmitting those vibrations through the air. But in space, those molecules don't exist in the same way. The near-perfect vacuum of space creates a truly silent environment. So, if you were floating in space, far from any planet or star, and you shouted, no one would hear you, not even the faintest echo. There are no air molecules to carry your voice, no vibrations to travel through. In essence, space is as silent as it gets. But while the vast silence of space may seem eerie, it is not a hindrance for astronauts. They have found ways to overcome the challenge of soundlessness. Astronauts communicate in space through radio waves, a form of electromagnetic radiation, which, unlike sound, doesn't need a medium to travel through. Radio waves can move through the vacuum of space. In fact, radio waves, along with other forms of electromagnetic radiation like light, X-rays, and microwaves, are crucial for all communication in space. These signals carry information across vast distances, from spacecraft to mission control and from astronauts to their families back on Earth. Astronauts use radio transmitters and receivers, which convert their voices into radio waves, allowing them to speak with people on Earth or their colleagues in nearby spacecraft. In addition to radios, spacesuits are equipped with communication systems. These systems allow astronauts to talk to each other, not just for conversations, but also for critical commands and safety instructions. Communication is essential in space, especially when astronauts are performing spacewalks or dealing with complex procedures. A simple slip or miscommunication can have life or death consequences in the extreme conditions of space. Therefore, despite the silence, these communication systems ensure that astronauts stay connected with one another and with mission control. Their suits have microphones that capture their speech, which is then converted into radio waves that transmit back to Earth. The silent nature of space also means that the sounds astronauts hear in their spacecraft are not the normal sounds we experience on Earth. The spacecraft itself makes a variety of sounds, such as the hum of the life support systems, the hiss of oxygen flowing, or the whir of equipment. But these sounds are very different from what we hear on Earth. They are artificial sounds created by technology, designed to keep astronauts alive and comfortable in a hostile, soundless environment. In fact, the lack of natural sound can create a sense of isolation or disorientation for astronauts. The silence outside is punctuated only by the hums and beeps of their equipment, making their experience in space uniquely quiet compared to life on Earth. Astronauts are trained to deal with the silence, as well as the occasional cacophony of mechanical noise that might accompany space exploration. This silence in space is not only an engineering challenge but also a psychological one. The isolation, the stillness, and the lack of the usual sounds we rely on to gauge our environment can have profound effects on astronauts. The silence of space, while comforting in some ways, can also make the distance from Earth feel even more vast and uncharted. There is a profound sense of quiet that envelopes everything in the void of space. A quiet that requires astronauts to adapt to new ways of perceiving the world. In a way, the silence of space mirrors the vastness of the universe itself. It serves as a reminder of how small and fragile we are in the grand scheme of the cosmos. It also highlights how incredible the ability to communicate and survive in such an environment truly is. The technology that enables astronauts to speak across the void of space is one of humanity's greatest achievements, allowing us to bridge the gulf between Earth and the farthest reaches of our solar system. For all the wonders of space, the stars, the planets, the galaxies, the absence of sound is one of the most striking features of the cosmos. It makes space feel otherworldly, as though we are drifting through a place where the rules of Earth no longer apply. The silence is not just a physical phenomenon, but a psychological one that places humanity in a quiet, vast, and uncharted wilderness. And yet, Despite this emptiness, the human spirit has found a way to make itself heard, to communicate, and to explore, all while surrounded by the profound silence of space. The coldest place in the universe, the Boomerang Nebula. In the vast reaches of space, where the familiar warmth of stars and planets fades into the darkness, there are places so cold that they defy everything we understand about temperature. One such place is the Boomerang Nebula, a stunningly beautiful but chillingly cold region of space, which holds the title of the coldest known natural place in the universe. The Boomerang Nebula, located about 5,000 light-years away from Earth in the constellation Centaurus, is a place where temperatures plunge to a staggering -458 degrees Fahrenheit, -272 degrees Celsius, just 1 degree above absolute zero. To understand just how cold that is, it's important to grasp the concept of absolute zero. Absolute zero, the lowest possible temperature in the universe, is the point at which all molecular motion comes to a halt. It's the theoretical limit where no heat or energy remains in matter. But the Boomerang Nebula is incredibly close to that limit, making it the coldest natural location we have discovered so far. The reason this nebula is so cold is linked to its unique nature and structure. The Boomerang Nebula is a protoplanetary nebula, meaning it represents a transitional phase in the life cycle of a dying star. The nebula is formed when a dying star expels its outer layers of gas and dust, creating a shell of material that slowly expands outward into space. The gas and dust in the Boomerang Nebula are being expelled at high speeds, about 800,000 kilometers per hour, 500,000 miles per hour, which causes a dramatic cooling effect. As the gas expands and thins out, it loses heat at an extraordinary rate, causing the temperature to drop rapidly. In fact, the cooling process is so efficient that it has created this region of space that is colder than any other known natural phenomenon. What makes the Boomerang Nebula so fascinating is that it doesn't just set a record for cold, it also tells us a great deal about the life cycle of stars and the dynamics of space. The formation of a protoplanetary nebula is a key stage in the evolution of dying stars, especially for those stars that are similar in size to our Sun. As a star reaches the end of its life, it expands into a red giant and eventually sheds its outer layers. This material then forms a nebula, which can last for thousands of years before the gas and dust disperse into space, leaving behind a white dwarf. The Boomerang Nebula represents one of the earliest stages of this process, where the gas is still very dense and the cooling effect is most pronounced. The extreme cold of the Boomerang Nebula is not just a fascinating scientific curiosity. It also presents challenges for astronomers studying it. To observe such a cold region, astronomers rely on infrared telescopes, as the nebula emits heat in the form of infrared radiation, which is invisible to the human eye but can be detected by sensitive instruments. By studying the infrared emissions from the Boomerang Nebula, scientists can learn more about the chemical composition of the nebula, the rate at which it is expanding, and the cooling process occurring within it. Despite the extreme cold, the Boomerang Nebula is a place of striking beauty. The nebula's shape, which resembles a boomerang, is a result of the gas and dust being ejected from the central star in two opposing directions, creating a symmetrical, curved shape. This gives the nebula its distinctive form, and it is one of the most well-known nebulae observed by astronomers. The cold, dense gases of the Boomerang Nebula are lit up by the dying star at its center, creating a vivid, colorful display of gas and light. These stunning colors, seen in infrared, reflect the chemical makeup of the nebula, hydrogen, carbon, and other elements that are critical for the formation of future stars and planetary systems. While the Boomerang Nebula is the coldest known natural place, it is not the only region of space that experiences extreme temperatures. Space itself, outside of nebulae and stars, is incredibly cold, with an average temperature of around -454 degrees Fahrenheit, -270 degrees Celsius, just a few degrees above absolute zero. However, most of the universe's cold regions are empty space, vast stretches of nothingness, where temperatures are low but not as extreme as those found in the Boomerang Nebula. The study of such extreme cold helps scientists understand more than just the coldness of space. It sheds light on the physics of gases, the behavior of particles in extremely low temperatures, and the formation of celestial bodies. The coldness of the Boomerang Nebula is an excellent laboratory for studying the dynamics of gas expansion and cooling, offering a unique opportunity to observe how matter behaves under extreme conditions. This research helps astronomers model other processes in the universe, such as the formation of planets, the evolution of stars, and the cooling mechanisms that govern the cosmos. Beyond its scientific importance, the Boomerang Nebula's extreme cold and beauty provide a humbling reminder of the vastness of the universe. Here, in the silent cold of space, a dying star's final breaths create a nebula that, while cold and inhospitable, contributes to the continuing cycle of stellar birth and death. Just as a star's death leads to the birth of new stars and planets, the Boomerang Nebula's story is part of the ongoing evolution of the cosmos, where matter is constantly being recycled and transformed into new forms. In the end, the Boomerang Nebula is a testament to the power and mystery of the universe. It reminds us that even in the coldest, most desolate parts of space, there is still beauty and wonder to be found. Its record-breaking cold, the product of gas expanding outward from a dying star, invites us to look deeper into the mechanisms that drive the evolution of stars and galaxies. The Boomerang Nebula is a place of extremes, a place where temperature reaches unimaginable lows, yet where the forces of the universe are still at work, shaping the very fabric of the cosmos. Galactic collisions and star formation. The universe is a place of constant motion, where galaxies collide, stars are born, and massive cosmic forces shape the very structure of the cosmos. Galactic collisions, in particular, are one of the most dramatic and awe-inspiring events that can take place in the universe. When galaxies collide, they don't just pass through one another. They interact, merge, and sometimes even transform into something entirely new. These collisions are responsible for the evolution of galaxies, creating new stars, new structures, and even new black holes. One of the most well-known galactic mergers in our cosmic neighborhood is the slow-motion collision between the Andromeda Galaxy and our own Milky Way. Andromeda, the largest galaxy in the local group, is currently on a collision course with the Milky Way. While this might sound catastrophic, it's important to remember that galaxies are made up mostly of empty space. The stars within these galaxies are so far apart that even during a collision, they won't physically collide. Instead, the gravitational forces at play during such an event will cause the galaxies to interact in dramatic ways. As Andromeda and the Milky Way draw closer to each other, their gravitational fields begin to affect one another. Stars in both galaxies will be tugged and stretched. Some may even be ejected from the galaxies entirely, while others may find themselves in new orbits. The collision will trigger intense star formation, as gas and dust clouds within the galaxies collide, causing them to compress and ignite new stars. These stars will be born in bursts of brilliance, creating clusters and nebulae, and filling the space between the galaxies with fresh light. Over the course of billions of years, the galaxies will continue to merge. Eventually, this slow-moving cosmic dance will result in the formation of a single, larger elliptical galaxy. While this process is happening on a vast timescale, it provides an essential insight into how galaxies evolve over time. Collisions between galaxies are not isolated events. They are an integral part of the life cycle of galaxies. These mergers help to build and shape galaxies, causing them to grow in size, alter their structure, and foster the creation of new stars. The formation of stars is another fascinating aspect of the evolution of galaxies. Stars, like everything else in the universe, are born from the collapse of gas and dust. This process begins when a giant cloud of gas and dust, called a nebula, begins to contract under its own gravity. As the material collapses, it heats up, and the pressure at the center increases, eventually leading to nuclear fusion. This fusion process is what powers stars, and it marks the birth of a new celestial body. In the early stages of a star's life, it is in a state of hydrostatic equilibrium, where the pressure from the nuclear fusion at its core balances the gravitational pull trying to collapse the star. This stability allows the star to shine steadily for millions to billions of years, depending on its size. For most stars, this period is the longest phase of their lives, during which they remain in the main sequence phase, fusing hydrogen into helium. However, stars don't remain in this stable phase forever. As a star consumes more of its fuel, the core begins to contract, and the outer layers expand. When a star exhausts its hydrogen fuel, it begins to fuse heavier elements, creating increasingly complex structures. This marks the beginning of the end for the star. Stars like our Sun will eventually evolve into red giants, swelling in size and shedding their outer layers to form planetary nebulae. The core, now composed mostly of carbon and oxygen, will cool and shrink into a white dwarf, a dense, hot remnant of the star that no longer undergoes fusion. Massive stars, however, follow a much more dramatic path. These stars burn through their fuel much faster than smaller stars. When a massive star runs out of fuel, it can no longer support the weight of its outer layers, and the core collapses in on itself, creating a supernova. This explosion is one of the most powerful events in the universe, releasing enormous amounts of energy and dispersing the elements created in the star's core into space. The supernova can trigger the formation of new stars in nearby regions, as the shockwave from the explosion compresses surrounding gas clouds. If the star is massive enough, the collapse of its core can lead to the formation of a black hole. A black hole, a region of space where gravity is so strong that nothing, not even light, can escape, is the final fate of the most massive stars. This collapse results in the creation of an object with infinite density, warping space-time around it in ways that challenge our understanding of physics. The formation of a black hole is a fascinating and mysterious event that marks the end of a star's life, but also the birth of a new type of object that can have profound effects on the surrounding space. Stars are not just the engines of energy in a galaxy. They are the building blocks of the universe. They create the elements that make up planets, life, and everything we see around us. The process of stellar evolution, how stars are born, live, and die, is one of the most important drivers of cosmic evolution. These cycles of birth and death not only shape the structure of galaxies, but they also contribute to the creation of the very materials that form planets, asteroids, and even life itself. The material ejected during supernova explosions, for example, enriches the interstellar medium with heavier elements like carbon, oxygen, and iron, which are essential for the formation of planets and the development of life. The evolution of stars is closely tied to the dynamic processes occurring within galaxies. Just as stars form, evolve, and die, galaxies go through cycles of growth, transformation, and interaction. The merging of galaxies and the birth of stars are intertwined in a continuous process of cosmic evolution. Each collision, each stellar birth, and each supernova explosion helps to shape the structure of the universe. Galaxies, stars, and their interactions provide the fundamental framework for understanding how the universe works on the largest scales. As we continue to explore the universe, the study of galactic collisions and star formation offers valuable insights into the forces that drive cosmic evolution. The ongoing merging of galaxies like Andromeda and the Milky Way, the birth of stars and nebulae, and the dramatic death of massive stars all contribute to the unfolding story of the universe. These processes have shaped the cosmos for billions of years and will continue to do so long into the future. The interplay between galaxies and stars, the cycles of creation and destruction, is what makes the universe a dynamic and ever-changing place, filled with both incredible beauty and profound mystery. Chapter 5: Cosmic Technology: How We Learn About Space. The development of space exploration. Space exploration has been one of humanity's most remarkable achievements. It is a story of curiosity, innovation, and the relentless pursuit of knowledge. The journey from the first telescopic observations of the night sky to landing humans on the moon and beyond is a tale filled with milestones that have changed the way we view our place in the cosmos. Every discovery, every spacecraft launched, and every astronaut who ventured into space has brought us closer to unlocking the mysteries of the universe. The first major breakthrough in space exploration came with the development of the telescope. In the early 1600s, Galileo Galilei turned a simple tube with lenses into one of the most powerful instruments ever created. His use of the telescope to observe the night sky transformed our understanding of the universe. Galileo's observations revealed that the Earth was not the center of the universe, as had been believed for centuries, but rather, our planet was part of a larger solar system. He discovered the moons of Jupiter, the phases of Venus, and the mountains on the moon, each revelation a stepping stone in our journey to understanding the vastness of space. Galileo's work was a precursor to many scientific advancements. His discoveries laid the groundwork for future astronomers to build upon, and it was the telescope that would continue to be the most essential tool in the search for knowledge about the universe. As time passed, advancements in telescope technology allowed us to peer deeper into space, unveiling distant stars, galaxies, and other celestial bodies. These observations ignited the imaginations of generations of scientists and space enthusiasts alike. The next significant leap in space exploration came in the early 20th century with the development of rockets. It was in the 1920s that rocket pioneers like Robert Goddard in the United States and Konstantin Tsiolkovsky in Russia began working on the technology that would eventually make space travel possible. Goddard, often called the father of modern rocketry, successfully launched the world's first liquid-fueled rocket in 1926. This breakthrough was essential in the creation of rockets powerful enough to leave Earth's atmosphere. By the 1950s, space exploration was on the cusp of a new era. The Cold War rivalry between the United States and the Soviet Union fueled the race to space, and both nations poured vast resources into space programs. In 1957, the Soviet Union achieved a groundbreaking success with the launch of Sputnik 1, the world's first artificial satellite. This small metal sphere orbiting the Earth was the beginning of the space age. Sputnik's success signaled that humans were capable of reaching beyond Earth's atmosphere, and it set the stage for even greater achievements. In response to Sputnik, the United States quickly ramped up its space program. In 1961, President John F. Kennedy made a bold commitment to land an American on the moon by the end of the decade. This declaration set the stage for one of the most ambitious projects in human history, NASA's Apollo program. The Apollo program would not only put a man on the moon, but also test the limits of human ingenuity, teamwork, and determination. The Apollo missions were a series of daring spaceflights designed to achieve Kennedy's goal. The Apollo 11 mission in July 1969 marked the culmination of these efforts. Astronauts Neil Armstrong and Buzz Aldrin became the first humans to land on the moon, while Michael Collins orbited above in the command module. Armstrong's famous words, "That's one small step for a man, one giant leap for mankind," echoed around the world as humanity took its first steps on another celestial body. This achievement was not just a victory for the United States, but for all of humankind, showing that the limits of what was possible had been pushed beyond anything previously imagined. However, space exploration didn't stop with the moon. The Apollo missions continued through the early 1970s, exploring more of the lunar surface and advancing our knowledge of space. Meanwhile, other countries began making significant contributions to space exploration. In 1971, the Soviet Union launched the first space station, Salyut 1, demonstrating the potential for long-term human presence in space. Over the decades, space stations like Mir, the International Space Station, ISS, and numerous other missions from nations around the world have advanced the study of microgravity, human biology, and the effects of prolonged space travel on the body. As the 20th century came to a close, the focus of space exploration shifted from lunar landings to the exploration of other planets. Robotic missions like the Mars rovers, Voyager spacecraft, and the Hubble Space Telescope allowed us to study the planets, moons, and distant stars. These unmanned missions provided invaluable data that reshaped our understanding of the solar system and the wider universe. The success of the Hubble Space Telescope, launched in 1990, provided breathtaking images of distant galaxies, nebulae, and star-forming regions. The data gathered from this telescope revolutionized our understanding of the cosmos, allowing us to peer back in time to see the early universe. While technology enabled us to explore distant worlds, it was the astronauts who carried the human spirit of exploration into space. Over the decades, many remarkable individuals have represented humanity's quest to explore the stars. From Yuri Gagarin, the first human to journey into space in 1961, to Valentina Tereshkova, the first woman to fly into space, to modern astronauts like Sally Ride and Mae Jemison, who broke barriers and made history in their own right, space exploration has been marked by incredible human achievement. Their courage and determination have inspired countless people around the world to look up at the stars and ask, What's next? One of the most significant astronauts in history was Neil Armstrong. His landing on the moon was not just a personal triumph, but a collective triumph for humanity. Armstrong, Aldrin, and Collins set foot on the moon during the Apollo 11 mission, but the legacy of their achievement continues to inspire future generations of explorers. Armstrong's words still resonate today, as they symbolize the incredible feat that humanity accomplished. The world of space exploration is vast, and the individuals who have pioneered this journey are as diverse as the stars they reach for. These pioneers didn't just travel into space. They expanded the boundaries of human knowledge, pushed the limits of technology, and embodied the spirit of exploration that drives us to continually look beyond our home planet. From early pioneers in telescopes to astronauts working on the International Space Station today, the history of space exploration is a testament to the power of human curiosity and ambition. As we move forward into the future, the next great milestones of space exploration await. The journey to Mars, the exploration of asteroids, and the search for life on other planets are just some of the exciting endeavors that will shape the next chapters of space exploration. And with new technologies, international collaboration, and growing interest from private companies, the future of space exploration looks brighter than ever. In the end, the development of space exploration is not just about technology. It is about the human spirit. It is about the desire to push the boundaries of what is possible, to explore the unknown, and to discover what lies beyond the horizon. The path of space exploration is one of discovery, one that will continue to unfold, revealing new mysteries and awe-inspiring wonders for generations to come. Space telescopes and instruments. The universe is vast, and understanding it requires looking far beyond the limits of our planet. For centuries, we have relied on telescopes to peer into the cosmos. These instruments have expanded our knowledge of the stars, the planets, and galaxies that make up our universe. However, the telescopes of the past, though groundbreaking, were limited by the technology of their time. Today, thanks to advancements in both ground-based and space-based telescopes, we are able to observe the universe like never before. Telescopes such as the Hubble Space Telescope, the James Webb Space Telescope, and the ongoing and upcoming missions to distant worlds are revolutionizing the way we understand the universe and our place in it. The Hubble Space Telescope, launched in 1990, marked a pivotal moment in space exploration. By being placed outside Earth's atmosphere, Hubble is free from the distortions caused by the atmosphere, which have limited ground-based telescopes for centuries. This unique vantage point allowed Hubble to capture images of the universe in unprecedented detail, bringing us closer to the farthest reaches of space. Its stunning images of distant galaxies, nebulae, and star-forming regions are some of the most iconic and influential visual representations of the cosmos. For more than 3 decades, Hubble has served as one of the most valuable tools for astronomers, helping to uncover the mysteries of space. One of the most significant contributions of the Hubble Space Telescope was its ability to measure the expansion of the universe. By observing distant galaxies, Hubble confirmed the rate at which the universe is growing, providing critical insights into the nature of dark energy, the mysterious force that is driving this expansion. Hubble also played a key role in our understanding of black holes, mapping the regions around supermassive black holes at the centers of galaxies, and even observing the formation of stars and planetary systems. While Hubble's contributions have been invaluable, the James Webb Space Telescope, launched in 2021, is set to take the exploration of space to an entirely new level. Unlike Hubble, Webb is equipped with infrared capabilities that allow it to see through cosmic dust clouds and observe objects that are too faint or too distant for Hubble to detect. This makes Webb an ideal tool for studying the earliest galaxies formed after the Big Bang, the formation of stars and planetary systems, and the atmospheric composition of exoplanets. Webb's larger mirror and advanced technology are already providing astronomers with data that was previously unimaginable, and it promises to change our understanding of the universe even further. Webb's instruments are designed to focus on the infrared portion of the electromagnetic spectrum, which means it can observe wavelengths of light that Hubble, with its visible and ultraviolet capabilities, could not. This makes it possible for Webb to peer through gas and dust, offering clearer views of star nurseries and galaxy formation. It also opens the door to studying the atmospheres of exoplanets, potentially identifying signs of life elsewhere in the cosmos. Webb's ability to study distant worlds in great detail is a significant leap forward in the search for extraterrestrial life, providing an unprecedented opportunity to understand the conditions necessary for life to thrive. While space telescopes like Hubble and Webb provide incredible visual data, understanding what we see requires specialized instruments that can analyze the light captured by these telescopes. Instruments like spectrometers play a crucial role in helping us understand the composition of stars, planets, and galaxies. Spectrometers break down light into its constituent wavelengths, allowing scientists to identify the elements that make up a celestial object. By studying the light emitted or absorbed by stars and planets, astronomers can determine their chemical composition, temperature, density, and even their motion. Spectrometers are used to study the light from stars to determine their age, size, and the processes occurring within them. By examining the spectrum of light emitted by a star, scientists can learn about the star's internal processes, such as nuclear fusion, and even predict its life cycle. This data also helps us identify the types of elements found in stars, some of which are critical to life as we know it, such as carbon, oxygen, and nitrogen. Spectroscopy also allows scientists to study the atmospheres of planets, both within our solar system and on distant exoplanets. By analyzing the light passing through a planet's atmosphere, spectrometers can reveal the presence of gases like oxygen, methane, and carbon dioxide. This information can tell us a great deal about the planet's potential to support life. For example, the presence of oxygen and methane together in a planet's atmosphere could be a sign of biological activity, as these gases are often produced by living organisms on Earth. Beyond spectroscopy, other instruments on space telescopes allow us to measure the physical properties of objects in space. Instruments like photometers and cameras help us measure the brightness of stars and galaxies, while detectors on space observatories like Webb and Hubble allow us to measure radiation across the entire electromagnetic spectrum. These instruments are not just capturing beautiful images, they are providing the data that helps astronomers solve some of the biggest questions about the universe, including how galaxies form, how stars evolve, and whether there are habitable planets beyond Earth. Another vital tool in space exploration is the ability to detect gravitational waves. Gravitational waves are ripples in spacetime caused by massive objects like black holes or neutron stars colliding. The detection of these waves has opened up a new window into the universe, allowing scientists to study cosmic events that were previously undetectable. The Laser Interferometer Gravitational Wave Observatory, LIGO, and other instruments are making it possible to hear the universe in a way we never could before. These waves provide an entirely new way to study black holes, neutron stars, and the fabric of space-time itself, revealing hidden aspects of the universe's most extreme phenomena. With each new instrument and mission, our understanding of space grows deeper. Space telescopes like Hubble, Webb, and upcoming missions are essential to our continued exploration of the cosmos. They allow us to peer into the distant past, studying galaxies that formed billions of years ago, and they provide the tools necessary to study the very building blocks of the universe. Instruments like spectrometers, photometers, and gravitational wave detectors enable scientists to decipher the complex language of the cosmos, helping us understand the composition of distant worlds and uncovering the mysteries of how the universe came to be. As we look to the future, the development of space exploration instruments promises to open even more doors to understanding the universe. The next generation of space telescopes will provide even greater detail and insight into the structure of galaxies, the formation of stars, and the potential for life on other planets. With advancements in technology, we are now able to study the universe in ways that were once unthinkable, from examining the atmospheres of exoplanets to detecting the faintest traces of ancient light from the dawn of the cosmos. Space exploration is no longer limited to just observing the stars. It's about actively understanding the very nature of space and time itself. As new missions and instruments take us further into the universe, we are continually refining our ability to answer the deepest questions about the origins of the universe, the existence of life, and the forces that shape everything from the smallest particles to the largest galaxies. Each discovery adds to the growing picture of the universe, helping us understand our place in the vast, expanding cosmos. Future technologies, exploring the next frontiers. As we stand on the brink of a new era in space exploration, the future promises to be as thrilling as the past has been transformative. The dreams of yesterday's pioneers are quickly becoming the realities of today, and with them, the boundaries of what's possible are continually expanding. From sending humans to Mars to searching for distant exoplanets, the next few decades are poised to bring breakthroughs that will fundamentally alter our understanding of the universe and our place within it. The idea of reaching Mars has long captured the human imagination. Mars, the fourth planet from the Sun, is a tantalizing target for exploration. With its similarities to Earth, its day length, its polar ice caps, and its seasons, Mars is the closest planet that could potentially support human life. NASA, SpaceX, and other organizations are working tirelessly to turn the dream of sending humans to Mars into a reality. It's no longer a matter of if we will go, but when. The first steps toward this ambitious goal are already underway. NASA's Artemis program, which aims to return humans to the Moon by 2025, will serve as a stepping stone for Mars exploration. By learning how to live and work on the Moon, scientists and engineers will gain valuable experience in the technologies needed to sustain human life in deep space. These lessons will be critical for future missions to Mars, which will take astronauts farther than humanity has ever gone before. Mars is not just a flyby destination. It's a world that demands sustainable habitation, reliable life support systems, and the ability to deal with challenges like radiation, low gravity, and long-term isolation. SpaceX, under the leadership of Elon Musk, has taken a bold approach to Mars exploration. Musk's vision for Mars colonization is based on the development of the Starship spacecraft, a fully reusable rocket that will be capable of carrying large numbers of astronauts and supplies to the Red Planet. SpaceX plans to make interplanetary travel not just feasible, but routine. The vision is for a self-sustaining colony on Mars, where humans can live, work, and thrive, potentially making humanity a multiplanetary species. Though these missions may be decades away, the technological advancements being made today are paving the way for this extraordinary leap. Mars missions, however, will not be limited to human exploration. Robotic spacecraft are already conducting in-depth studies of the Martian surface. Rovers like Perseverance and Curiosity are searching for signs of ancient life, analyzing the composition of the Martian soil, and testing technologies that will help humans survive on the planet. Future missions will build on this work, sending more advanced rovers and landers to gather even more data on Mars's geology, atmosphere, and potential for habitability. But while Mars is an immediate goal for space agencies, the search for exoplanets, planets orbiting stars outside our solar system, represents a new frontier in space exploration. As of now, thousands of exoplanets have been discovered, but most are too far away to study in detail. The next generation of space telescopes, such as the James Webb Space Telescope, will provide unprecedented views of exoplanets, allowing us to study their atmospheres, weather systems, and perhaps even find signs of life. The search for exoplanets has already yielded some incredible discoveries. For instance, scientists have found Earth-like planets in the habitable zone, where conditions could be just right for liquid water to exist. Some of these planets are so similar to Earth that they offer a glimpse into what might exist on distant worlds, and the possibility of finding life beyond our planet is becoming more plausible. The study of exoplanets is not just about understanding other worlds, it's about understanding our own world in a broader context. By studying planets with similar conditions to Earth, we can learn more about the origins of our planet and the conditions that make life possible. To search for life on other planets, one of the most promising methods is the study of biosignatures. These are molecules or patterns of light that could indicate the presence of life, either microbial or advanced. Instruments like the James Webb Space Telescope, with its infrared capabilities, are specifically designed to study the atmospheres of exoplanets, searching for chemical imbalances that might suggest biological processes. For example, the combination of oxygen and methane in a planet's atmosphere could indicate the presence of living organisms, since these gases tend to coexist only in the presence of life. Detecting these biosignatures would be one of the most profound discoveries of the 21st century, transforming our understanding of the universe and our place in it. While the exploration of Mars and exoplanets represents our next big steps in space exploration, the dream of interstellar travel remains the final frontier. Interstellar travel. The idea of traveling to other stars seems like science fiction, but it is slowly becoming a topic of serious scientific discussion. The nearest star system to Earth, Alpha Centauri, is more than 4 light-years away, which makes traveling there with current technology unfeasible. But that hasn't stopped scientists and visionaries from considering how we might one day make such a journey possible. One concept gaining attention is the idea of using advanced propulsion systems, such as nuclear fusion or antimatter drives, to achieve speeds fast enough to make interstellar travel a reality. The challenge is immense. The distances are so vast that even the fastest spacecraft we have today would take thousands of years to reach another star. But scientists are exploring new ways to generate the necessary speeds, and breakthroughs in materials science, energy production, and propulsion could one day make interstellar travel possible. In the coming decades, we may see the development of prototype technologies that allow for faster, more efficient travel within our own solar system, which could be the first step toward interstellar exploration. One of the most ambitious plans for interstellar travel is the Breakthrough Starshot Initiative, a project that aims to send small, light-powered spacecraft to Alpha Centauri within the next few decades. The goal is to send hundreds of tiny, light-powered probes, each no larger than a small chip, to the star system. These probes would travel at speeds up to 20% of the speed of light, powered by laser beams from Earth. While this project is still in its early stages, it marks the beginning of a new era in space exploration, one in which humanity could one day reach out and touch the stars. These ambitious missions are just the beginning. Future space technologies will continue to evolve, allowing us to explore the farthest reaches of our solar system, study the mysteries of distant planets, and potentially even travel to other star systems. With advancements in artificial intelligence, robotics, and propulsion, the possibilities for space exploration are truly limitless. As technology progresses, we will continue to uncover new ways to explore the cosmos and answer some of the biggest questions humanity has ever asked. Are we alone in the universe? What lies beyond our solar system? And what is the future of human exploration in the cosmos? The future of space exploration is not just about sending spacecraft to distant worlds. It's about expanding our understanding of the universe and pushing the boundaries of what we can achieve. Whether it's landing humans on Mars, searching for life on exoplanets, or venturing to the stars, the next chapter in space exploration is unfolding before our eyes. As we develop the technologies to explore these far-off destinations, we are not just traveling to new worlds. We are advancing as a species, becoming a part of something far greater than ourselves, and taking our first steps toward becoming a multiplanetary civilization. Chapter 6: Space Exploration, the Human Connection. The space race and its legacy. The space race was more than just a competition between two superpowers. It was a race that united humanity in its shared quest to explore the unknown. The Cold War rivalry between the United States and the Soviet Union set the stage for one of the most thrilling chapters in human history: the race to conquer space. This intense period of scientific achievement, political maneuvering, and technological advancement would lead to groundbreaking missions that forever altered our understanding of the cosmos and our place in it. The Cold War was not just a political struggle. It was a battle for prestige, influence, and technological superiority. As the Soviet Union and the United States sought to assert their dominance on the global stage, space became the ultimate frontier. The first major victory in the space race came in 1957, when the Soviet Union launched Sputnik 1, the world's first artificial satellite. This small metallic sphere, orbiting the Earth, was a clear sign that the Soviets had the ability to reach into space. The world watched in awe, and the United States, under President Dwight D. Eisenhower, quickly recognized the need to respond. The launch of Sputnik marked the beginning of an era where every step in space exploration was followed with intense scrutiny and national pride. The United States, determined to catch up, established NASA, the National Aeronautics and Space Administration, in 1958. It was not just a government agency, It was a symbol of American resolve to match the Soviet achievements in space. NASA's goal was to send humans into space, reach the moon, and demonstrate the power of American technology. But the task ahead was immense, and the challenges were staggering. The United States' first attempts were met with a series of failures. Early space missions, such as the Vanguard satellite launch, did not go as planned. But by the early 1960s, the United States made a breakthrough. In 1961, President John F. Kennedy made his now famous speech before Congress, declaring that the United States would land a man on the moon before the end of the decade. His words electrified the nation, marking a turning point in the space race and setting the stage for what would become one of the greatest technological and human achievements in history. This ambition was realized in 1969 with the successful Apollo 11 mission, in which two American astronauts, Neil Armstrong and Buzz Aldrin, became the first humans to set foot on the moon. Armstrong's words, "That's one small step for man, one giant leap for mankind," were heard around the world, marking the end of the space race and securing a lasting legacy for the United States. The Apollo moon landings were not just a victory for the United States. They were a victory for all of humanity. They showed that, with determination and ingenuity, humans could reach beyond their home planet and explore the cosmos. The Apollo program, which continued with a total of 11 manned missions to the moon, not only advanced our understanding of the moon, but also spurred technological advancements that would impact nearly every aspect of modern life. The space race was about more than just reaching the moon. It was about pushing the boundaries of what humanity could achieve. The technologies developed during this time laid the groundwork for modern computers, telecommunications, and materials science. The race to space pushed forward research in every scientific discipline and spurred innovation in ways that would benefit generations to come. But the space race was not solely about the United States. The Soviet Union also made significant strides during this period, with their own legendary achievements. In 1961, Soviet cosmonaut Yuri Gagarin became the first human to travel into space, orbiting the Earth aboard Vostok 1. Gagarin's achievement was a momentous event, marking the first time that a human had escaped the confines of our planet and ventured into the vastness of space. Gagarin's flight was a symbol of Soviet technological prowess, and his success was celebrated by millions of people around the world. He became a national hero in the Soviet Union and an international symbol of the possibility of human space exploration. Following Gagarin's historic flight, the Soviets went on to make further advancements in space exploration, including the first woman in space, Valentina Tereshkova, who flew in 1963, and the first space station, Salyut 1, launched in 1971. These milestones were a testament to the Soviet Union's commitment to space exploration, and they continued to push the boundaries of what was possible during the Cold War. Yet, even with these achievements, the United States' successful landing of humans on the moon ultimately defined the outcome of the space race. The Apollo program represented the culmination of a decade of work, sacrifice, and collaboration. It not only demonstrated American technological and scientific leadership, but also inspired the world. The moon landing was a defining moment in history, a triumph of human ingenuity that captured the imagination of millions. The legacy of the space race is far-reaching. It demonstrated that when nations collaborate, when human potential is harnessed to its fullest, extraordinary things can happen. It also laid the foundation for the global space programs that we have today. The United States, the Soviet Union, and other countries continue to build upon the advances made during the Cold War era, working together on projects like the International Space Station, ISS, a shining example of international collaboration in space. In addition to the political and technological impact, the space race also had a profound effect on the public. The space race captured the imagination of an entire generation, inspiring countless individuals to pursue careers in science, engineering, and technology. It sparked interest in space that continues to this day, with new generations of scientists, astronauts, and space enthusiasts eager to continue the exploration of space. Beyond the astronauts and the space missions themselves, there are the enduring lessons of the space race. It showed us that the limits of human potential are not defined by geography or national borders, but by our collective will and vision. It demonstrated that no challenge is too great, and no dream is too far-fetched. It pushed humanity to the edge of possibility and set the stage for future space exploration efforts, such as the missions to Mars, the study of exoplanets, and the ongoing quest to understand the cosmos. In the legacy of Neil Armstrong, Yuri Gagarin, Sally Ride, and all the astronauts and pioneers of the space race, we see the power of human curiosity, courage, and perseverance. These pioneers did not just break records, they broke the boundaries of what was thought to be possible. Their achievements serve as a reminder that, in the pursuit of knowledge and discovery, humanity is always capable of reaching new heights, exploring new frontiers, and rewriting the very laws of what we can achieve. The space race, though a product of its time, laid the groundwork for the future of space exploration, a future that continues to evolve with each new mission, each new discovery, and each new generation of space pioneers. The space race is far from over. In fact, it is only just beginning. As we prepare to venture to Mars, search for life beyond Earth, and even consider interstellar travel, we are following in the footsteps of those who dared to dream of a future beyond the stars. The legacy of the space race lives on in every spacecraft we send into the void, in every new technology that extends our reach into the cosmos, and in the ongoing drive to explore the unknown. The greatest achievements in space exploration still lie ahead, and the lessons learned from the space race will continue to guide us as we reach for the stars. The search for extraterrestrial life. The search for extraterrestrial life is one of the most profound quests in the history of science and exploration. For centuries, humans have looked up at the stars and wondered if we are alone in the universe. That question has fueled imaginations, driven scientific research, and inspired countless missions to explore the stars. Today, we stand on the cusp of new discoveries that could fundamentally change our understanding of life, not just on Earth, but across the vast expanse of the cosmos. One of the most significant developments in the search for extraterrestrial life is the discovery of exoplanets, planets that exist outside our solar system. In the past few decades, astronomers have discovered thousands of these distant worlds, many of which exist in what is known as the habitable zone of their star. The habitable zone is the region around a star where conditions might be just right for liquid water to exist, one of the key ingredients for life as we know it. This discovery has opened up a new frontier in the search for life beyond Earth, as scientists now know that there are potentially millions of planets in our galaxy alone that could harbor life. The Kepler Space Telescope, launched by NASA in 2009, was a game-changer in this search. By monitoring the brightness of distant stars, Kepler was able to detect tiny dips in light caused by planets passing in front of them. This method, called the transit method, allowed scientists to find and confirm thousands of exoplanets. Many of these exoplanets orbit stars similar to our Sun, and some of them are located in the habitable zone, where temperatures might be conducive to liquid water. These findings have made the prospect of discovering extraterrestrial life feel more tangible than ever. In addition to Kepler, the James Webb Space Telescope, launched in 2021, is poised to provide even more detailed observations of exoplanets, especially their atmospheres. Webb's infrared capabilities will allow scientists to analyze the chemical composition of these distant worlds and potentially detect signs of life. By studying the light passing through an exoplanet's atmosphere, Webb could help identify gases such as oxygen, methane, and carbon dioxide, gases that, on Earth, are often associated with biological processes. The presence of such gases could be a significant clue in the search for life beyond our planet. However, while the discovery of exoplanets in the habitable zone is exciting, it's not enough to prove that life exists elsewhere. For that, scientists have turned to other methods of investigation, including the search for alien signals. The search for extraterrestrial intelligence, or SETI, is an ongoing effort to listen for signals from intelligent civilizations in the universe. SETI uses radio telescopes to scan the skies for narrow-bandwidth radio signals, signals that could potentially be produced by extraterrestrial technology. The idea behind SETI is simple. If intelligent alien civilizations exist, they might be sending signals into space, either intentionally or unintentionally. Radio waves travel through space at the speed of light, and a narrow bandwidth signal could be a sign of technology similar to our own. While SETI has not yet detected any definitive signals from extraterrestrial civilizations, the search continues. In fact, the discovery of even a single alien signal would be one of the most significant events in human history, confirming that we are not alone in the universe. Over the years, there have been many instances of intriguing signals detected by radio telescopes, such as the famous WOW signal detected in 1977. This signal, which lasted for about 72 seconds, has never been fully explained. While some scientists believe it could be the result of natural phenomena, others remain convinced that it could be a sign of extraterrestrial intelligence. Despite the lack of conclusive evidence, SETI has been invaluable in sparking global interest in the possibility of intelligent life elsewhere. In addition to radio signals, scientists are also looking for other forms of communication that might exist. For example, some researchers have proposed that advanced civilizations might use laser beams to send information across interstellar distances. This concept, known as optical SETI, suggests that rather than using traditional radio waves, extraterrestrial civilizations might be using highly focused beams of light to communicate. While this idea is still in its infancy, it demonstrates the wide range of possibilities that scientists are exploring in the search for extraterrestrial life. Meanwhile, the discovery of microbial life elsewhere in the solar system could provide another vital clue. Mars, Europa, one of Jupiter's moons, and Enceladus, one of Saturn's moons, are all considered prime candidates for hosting microbial life. These worlds may not have the conditions for complex life forms, but they could harbor simpler organisms, such as bacteria or microbes, that have adapted to their harsh environments. In recent years, missions like NASA's Perseverance rover and the European Space Agency's ExoMars program have been designed to search for signs of ancient life on Mars, while future missions to Europa and Enceladus will focus on studying their subsurface oceans, where life could potentially exist. The search for microbial life within our own solar system is closely tied to the ongoing study of astrobiology, the field of science that investigates the potential for life elsewhere in the universe. Astrobiologists study extreme environments on Earth, such as deep-sea vents, hot springs, and acidic lakes, where life thrives despite conditions that would be hostile to most organisms. These studies help scientists understand the types of environments where life might exist on other planets or moons. By examining the adaptability of life on Earth, scientists can begin to narrow down the types of environments to look for when searching for extraterrestrial life. As we continue to develop new technologies and methods for exploring the cosmos, our ability to detect signs of life will improve. New space telescopes, such as the upcoming Nancy Grace Roman Space Telescope, will provide even more detailed observations of exoplanets, potentially uncovering signs of life or conditions conducive to life. Ground-based telescopes and observatories around the world are also playing a crucial role in this search, continuously scanning the skies for new exoplanets and conducting atmospheric studies. The question of whether we are alone in the universe is one that has captivated humanity for centuries. As we look to the stars, our ability to find answers to this question grows stronger with each passing year. The discovery of exoplanets, the ongoing search for alien signals, and the study of microbial life on nearby planets are just the beginning of what could be an exciting chapter in human history. While we have yet to find definitive evidence of extraterrestrial life, the ongoing efforts to answer this question have already led to groundbreaking discoveries and technological advancements that will shape the future of space exploration. The search for extraterrestrial life is more than just a scientific endeavor. It is a reflection of humanity's unrelenting curiosity and desire to understand the universe. It speaks to our innate need to explore the unknown and to find our place in the vast, unfathomable cosmos. Whether through the study of distant exoplanets, the search for alien signals, or the exploration of the moons of our own solar system, the search for life beyond Earth will continue to drive space exploration for generations to come. In the end, the search for extraterrestrial life is not just about finding alien civilizations. It's about discovering more about our own planet, our own origins, and the very nature of life itself. It is a quest that transcends the boundaries of science and touches the very essence of what it means to be human. To explore, to seek, and to understand the mysteries of the universe. Human habitation in space. The idea of humans living and working in space, far beyond the safety of Earth's atmosphere, is no longer a distant dream. It is rapidly becoming a reality. Over the past few decades, advancements in space technology and international collaboration have made it possible for humans to live and work in space for extended periods. The International Space Station, ISS, which has been continuously occupied since 2000, stands as a testament to humanity's capacity to adapt to life in the harsh environment of space. It is a symbol of what we can achieve when nations come together to explore the cosmos, and it offers us invaluable insights into what the future of human habitation in space might look like. The ISS, orbiting Earth at an altitude of approximately 400 kilometers, serves as a microgravity laboratory where scientists conduct experiments in physics, biology, and material science, fields that are impossible to study under the conditions we experience on Earth. The astronauts aboard the ISS are not just researchers. They are pioneers, enduring the psychological and physical challenges of space to help pave the way for future human exploration of Mars and beyond. The station has been home to astronauts from numerous countries, and through this international cooperation, the ISS has become a symbol of unity in the pursuit of knowledge. For the astronauts aboard the ISS, every day is an extraordinary test of human endurance. The space station orbits Earth roughly every 90 minutes, providing its crew with 16 sunrises and sunsets each day. In the confined quarters of the station, astronauts must work together, live together, and maintain the complex systems that keep them alive. They conduct experiments that can only be done in the microgravity environment of space, such as studying how human muscles and bones react to long periods of weightlessness, or growing plants in conditions that would be impossible on Earth. But life on the ISS isn't without its challenges. For one, the lack of gravity affects nearly every part of an astronaut's body. In the absence of weight-bearing activity, bones weaken, muscles atrophy, and the cardiovascular system becomes less efficient. These physical changes are monitored closely by scientists to better understand how long-term space travel might affect the human body and to develop countermeasures to keep astronauts healthy. Bone density loss, muscle weakening, and the reduction in the size of heart muscles are some of the most serious issues facing astronauts on extended missions. Another challenge astronauts face in space is the psychological impact of isolation. In space, there is no escape from the confined environment of the spacecraft or station. The crew members are thousands of kilometers away from their families, friends, and the comforting presence of Earth. The psychological effects of this isolation are real and can be intense. Astronauts must learn to cope with the monotony, the absence of natural day-night cycles, and the stress of living in close quarters with a small group of people for months at a time. The isolation can lead to depression, anxiety, and interpersonal conflicts, which is why astronaut training includes psychological preparation and strategies for dealing with stress. The long durations of space missions, which can last 6 months or longer, also affect an astronaut's sleep cycle. The lack of a natural day-night rhythm, combined with the constant exposure to light as the ISS orbits Earth, disrupts normal sleep patterns. To address this, astronauts use sleep aids such as eye masks, sleeping bags, and specific lighting conditions designed to help them get restful sleep. Despite these efforts, the quality and quantity of sleep can still be compromised, leading to fatigue, which further complicates their work and their health. As we look to the future, the challenges of long-term space travel will only become more complex, particularly with plans to send humans to Mars. The mission to Mars is one of the most ambitious undertakings humanity has ever planned. Unlike the ISS, which orbits relatively close to Earth, Mars is millions of kilometers away, meaning a round-trip mission could take several years. This introduces new levels of difficulty. The crew will be isolated not just from their families, but from the entire world. They will be far beyond the reach of rescue missions or resupply efforts, making self-sufficiency a critical necessity. For a human mission to Mars, everything will need to be meticulously planned and carefully engineered. The spacecraft must be capable of providing a livable environment for the astronauts, with systems for water, air, food, and waste management. Radiation protection will be a top priority, as the astronauts will be exposed to much higher levels of radiation than they would be on Earth or in low Earth orbit. The spacecraft will need to have effective shielding to protect against solar radiation and cosmic rays. both of which can be harmful in the long term. Astronauts on a Mars mission will also face significant challenges with regard to their physical health. Prolonged exposure to microgravity will continue to cause muscle atrophy and bone density loss, but the issue will be compounded by the long travel time and the lack of immediate medical support. Doctors on Earth will monitor the astronauts' health, but they will have limited ability to intervene in the event of a medical emergency. This makes it essential to develop medical technologies capable of diagnosing and treating conditions on Mars, or perhaps even advanced robotics that could assist in performing surgery if needed. In addition to the physical challenges, the psychological strain on astronauts will be even more intense on a Mars mission. Unlike the ISS, where astronauts can communicate relatively easily with loved ones on Earth, a mission to Mars will involve communication delays of up to 20 minutes one way, meaning astronauts will be isolated from their families and from Earth's social networks for extended periods. The mental and emotional toll of such isolation will need to be carefully managed, and future Mars missions will likely include extensive psychological support systems. Space agencies will need to ensure astronauts have the mental fortitude to handle long stretches of solitude, as well as the ability to resolve conflicts in close quarters without access to external help. While the physical and psychological challenges of long-term space travel are daunting, they are not insurmountable. Researchers are already developing innovative solutions to address these issues. For example, new exercise regimens and countermeasures like resistance training and advanced medical monitoring systems are being tested on the ISS to prevent muscle and bone loss. Similarly, mental health support, including virtual reality and cognitive training, is being explored to help astronauts cope with isolation and stress. As we prepare for the future of human space exploration, the success of the ISS has laid the groundwork for the journey to Mars. The knowledge gained from living and working in space for extended periods is invaluable, and it is this knowledge that will allow us to send astronauts to Mars and beyond. The astronauts aboard the ISS are not just exploring space. They are pioneers, laying the foundation for future generations to venture further into the cosmos. Ultimately, human habitation in space is not just about surviving in the vacuum of space. It's about learning how to thrive, how to adapt, and how to live in harmony with the environment of space. Whether on the ISS or a future Mars colony, the challenges of space travel will push the limits of human endurance and creativity. But with each challenge overcome, we take one step closer to becoming an interplanetary species, capable of exploring the stars, expanding our horizons, and unlocking the secrets of the universe. The journey ahead is long and difficult, but the rewards will be immeasurable, not just for the astronauts who will make these historic journeys, but for all of humanity. Chapter 7: Mysteries of the Universe, What We Don't Know. The Big Bang and the Origin of the Universe. The story of the universe begins with an event so powerful, so immense, that it reshaped everything we know about time, space, and matter. The Big Bang. This singular explosion, occurring around 13.8 billion years ago, was not just a moment of creation, it was the birth of everything. It set the stage for the formation of stars, galaxies, and ultimately the cosmos as we know it. From this fiery origin, all that exists in the universe, the planets, the stars, the black holes, was born. But despite our progress in understanding the Big Bang, many mysteries remain about the true origins of the universe, and new theories continue to challenge our understanding of time, space, and the very fabric of reality itself. At the core of our understanding lies the theory of the Big Bang. It suggests that the universe began as an infinitely small, infinitely dense point, sometimes called a singularity. From this point, space itself began to expand rapidly in an event known as cosmic inflation. This initial burst of energy and matter gave rise to the universe, which continues to expand even today. The aftermath of this explosion set the conditions for the formation of particles, atoms, stars, galaxies, and eventually the Earth and all the other cosmic bodies we see today. This theory has been supported by a range of evidence, one of the most compelling being the discovery of the cosmic microwave background, CMB, radiation. The CMB is the faint, uniform glow that fills the entire universe and is considered the afterglow of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is a snapshot of the universe when it was just 380,000 years old. This radiation provides a picture of the universe's infancy and gives scientists vital information about how the universe began and how it evolved. Another piece of evidence supporting the Big Bang theory comes from the observation of the redshift of distant galaxies. When we look at distant galaxies, we see that their light is stretched toward the red end of the spectrum, a phenomenon known as redshift. This redshift occurs because galaxies are moving away from us as the universe expands. The fact that we can observe this redshift in galaxies throughout the universe gives us direct evidence of the ongoing expansion of the universe, which traces back to the Big Bang. Despite this overwhelming evidence, the true nature of the Big Bang and what happened before it remains one of the most profound mysteries in cosmology. For decades, scientists have sought to understand not only what happened during the Big Bang, but also why it happened and what triggered it. What came before the Big Bang? Was there a time before time, or is time itself a result of the Big Bang? One of the biggest questions surrounding the origin of the universe is the concept of the multiverse. The idea that our universe is just one of many, each existing independently in its own bubble or pocket of space-time, has captured the imaginations of scientists and philosophers alike. According to some theories, the Big Bang may not have been the beginning of all things. Rather, it could have been the beginning of our particular universe, a single bubble in an infinite multiverse of universes. Each of these universes could have its own set of physical laws, constants, and even dimensions of space and time. This concept challenges everything we know about the uniqueness of our universe and opens up questions about the very nature of existence itself. The multiverse theory has sparked intense debate among cosmologists. Some scientists believe it provides an elegant explanation for the fine-tuning of the universe. Why do the physical constants of our universe appear so perfectly calibrated for the existence of life? In a multiverse, our universe might simply be one of many that just happens to have the right conditions for life, while other universes may not. Others, however, question the multiverse theory because it suggests that other universes are beyond our reach, making them impossible to observe or test. As a result, the idea remains speculative, but it continues to challenge our understanding of reality. The exploration of the Big Bang and the multiverse is deeply connected to our quest to understand dark matter and dark energy. These mysterious substances make up most of the universe's mass-energy content, yet they remain elusive. Dark matter, which is thought to be responsible for the gravitational effects seen in galaxies and galaxy clusters, interacts with ordinary matter only through gravity and possibly weak forces. Dark energy, on the other hand, is thought to be driving the accelerated expansion of the universe. Together, these invisible forces are integral to our understanding of the universe's origin and its ultimate fate. Current theories propose that dark matter and dark energy may have played a critical role in shaping the universe after the Big Bang. In fact, the early universe was dominated by these mysterious forces. Understanding how dark matter and dark energy came into existence and how they have influenced the expansion of the universe is key to understanding the Big Bang itself. Could dark matter have been created during the first moments of the universe, or did it emerge later as the universe cooled and expanded? The search for answers to these questions is ongoing. New telescopes, such as the James Webb Space Telescope, and experiments like the Large Hadron Collider are working to uncover the nature of dark matter and dark energy. These cutting-edge instruments allow scientists to peer deeper into the universe's history, tracing the evolution of galaxies and stars back to their formation. By studying the cosmic microwave background radiation, scientists hope to learn more about the first few moments of the universe's existence and potentially uncover clues about what came before the Big Bang. The idea of the multiverse also ties into the study of quantum mechanics and string theory. These theoretical frameworks suggest that the fundamental building blocks of the universe may not be particles, but tiny vibrating strings that exist in multiple dimensions. Some versions of string theory propose that our universe is just one of many possible configurations of strings, each leading to different physical laws and constants. If this theory is correct, the Big Bang could have been the result of a fluctuation in a higher dimensional space, giving birth to the universe we know today. Another theory that has emerged in recent years is the idea of cyclic or oscillating universes. According to this model, the universe undergoes an endless series of expansions and contractions, with each Big Bang followed by a big crunch, where the universe collapses in on itself before expanding again. In this model, the universe we inhabit is just the latest cycle in a series of eternal rebirths. While this theory offers an elegant solution to the problem of what happened before the Big Bang, it also faces significant challenges in terms of observational evidence and theoretical consistency. The question of what caused the Big Bang is one that continues to elude scientists. Was it a spontaneous event, a singularity that simply erupted into existence? Or was there some deeper, more fundamental cause? A fluctuation in the quantum field, a collision between universes, or a triggering event in a higher dimension? As we advance in our understanding of physics, these questions may eventually be answered, but for now, the origin of the universe remains one of the greatest unsolved mysteries in science. In conclusion, the Big Bang theory remains the cornerstone of our understanding of the universe's origin. It has provided a framework for explaining the formation of galaxies, stars, and planets, as well as the expansion of the universe itself. However, the mysteries of the Big Bang, the multiverse, and the true nature of the universe's origins continue to challenge scientists. As our knowledge deepens and our technological tools improve, we are likely to unlock even more secrets of the universe's past, and perhaps gain a clearer understanding of the forces that shaped the cosmos. Until then, the search for answers continues as we strive to understand the very beginning of everything. Unsolved cosmic mysteries. The universe is vast, full of wonder, yet still shrouded in profound mysteries. While we have made great strides in understanding the cosmos, some questions remain unanswered, questions that challenge the very nature of reality itself. The hunt for answers to these cosmic mysteries not only drives scientific exploration, but also sparks the imagination of anyone seeking to understand the universe in its most enigmatic forms. In this chapter, we'll delve into some of the most perplexing unsolved mysteries in modern astrophysics, mysteries that may take decades, centuries, or even longer to fully unravel. One of the greatest cosmic puzzles is the mystery of antimatter. According to the laws of physics, for every particle of matter in the universe, there should be an equal and opposite particle of antimatter. When these particles collide, they should annihilate each other, releasing vast amounts of energy. But when we look out into the universe, something is missing. There's far more matter than antimatter. In fact, the universe appears to be predominantly made of matter, with antimatter being almost entirely absent. This imbalance is one of the most profound questions in modern physics. Why is there more matter than antimatter? Where did the antimatter go? The answer to this question remains elusive. Some scientists speculate that during the earliest moments of the universe, the Big Bang produced equal amounts of matter and antimatter. However, for reasons not yet understood, a slight excess of matter over antimatter occurred. This tiny imbalance, less than 1 part in a billion, was enough to lead to the formation of the universe we see today. But the process that caused this imbalance remains a mystery. The search for an answer is ongoing, with experiments at particle accelerators like the Large Hadron Collider and various theoretical models suggesting possible explanations. Some believe that the answer may lie in the fundamental symmetry of the laws of physics. Perhaps there's a deeper mechanism at work that we don't yet understand. This mystery could hold the key to one of the most significant questions in cosmology. How did our universe come to be so dominated by matter, and what happened to the antimatter? Then, there's the even more elusive mystery of dark matter and dark energy. Together, these two phenomena account for nearly 95% of the total mass-energy content of the universe, yet we cannot see them, touch them, or directly detect them. In fact, we only know they exist because of their gravitational effects on visible matter. Dark matter is thought to be a form of matter that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. We infer its presence by the way galaxies spin and by how light from distant objects is bent as it passes through galactic clusters, an effect known as gravitational lensing. Yet, despite decades of research, scientists still don't know what dark matter is made of. Several leading theories suggest that dark matter could be composed of weakly interacting massive particles, WIMPs or axions, but no definitive detection has been made. The hunt for dark matter continues in laboratories around the world, with detectors buried deep underground or placed in space, all aimed at finding evidence of these mysterious particles. Understanding dark matter is essential because it could explain not just the formation of galaxies, but also the very structure of the universe itself. Without dark matter, galaxies would not have the mass to hold them together, and the universe, as we know it, could not have evolved the way it has. Dark energy, the second component of this cosmic conundrum, is even more mysterious. Dark energy is believed to be responsible for the accelerated expansion of the universe. Since the late 1990s, observations of distant supernovae have shown that the universe is expanding at an ever-increasing rate, a discovery that completely changed our understanding of the cosmos. Before this, scientists believed the expansion of the universe was slowing down due to gravity. Instead, it turns out that something is causing the universe to expand faster and faster, something that scientists call dark energy. Dark energy makes up about 68% of the total energy in the universe, but we still don't know what it is or how it works. Some theories suggest that dark energy is a property of space itself, a form of energy that is intrinsic to the fabric of the cosmos. Others propose that it could be linked to quantum fluctuations in empty space. Still, others believe it could be a sign that our understanding of gravity and general relativity needs to be revised. The mystery of dark energy is one of the most pressing challenges in modern cosmology, and solving it could unlock a deeper understanding of the universe's structure and its eventual fate. The existence of dark matter and dark energy raises even more profound questions about the nature of the universe. If such unseen forces dominate the cosmos, what does that tell us about the fundamental laws of physics? Are there other forces and particles yet to be discovered, waiting to be understood? Will the next great breakthrough in physics reveal a deeper connection between gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, forces that, up until now, have remained separate and distinct in the standard model of particle physics? And, perhaps even more fundamental, how do these unseen forces affect the fate of the universe? Theories range from the concept of a big freeze, where the universe continues expanding indefinitely, to the big crunch, in which the universe might eventually collapse in on itself. There's also the possibility of a big rip, where the accelerated expansion due to dark energy could ultimately tear apart galaxies, stars, and even atoms. These possibilities might be far in the future, but the discovery of dark matter and dark energy gives us clues about how the universe might end, if such an end exists. As researchers continue to probe the nature of dark matter and dark energy, they are also exploring the very structure of space-time itself. Quantum mechanics and general relativity, the two pillars of modern physics, have proven to be fundamentally incompatible in certain extreme conditions, such as near black holes or at the beginning of the universe. The search for a theory of quantum gravity, one that can reconcile these two theories, is one of the most important challenges facing physicists today. Will we discover a unified theory that can explain all the forces of nature? Will this theory lead to a deeper understanding of the origins of the universe? We also face questions about the larger-scale structure of the universe. For example, astronomers have detected vast cosmic voids, enormous, seemingly empty regions of space where galaxies and stars are scarce. These voids, which are far larger than any superclusters of galaxies, challenge our understanding of the uniformity of the cosmos. What caused these voids, and why do they exist? Could the presence of dark matter or dark energy play a role in their formation? And do they tell us something about the shape and fate of the universe? While we are uncovering the answers to some of these questions, others remain tantalizingly out of reach. The mysteries of the universe, what happened before the Big Bang, what the true nature of dark matter and dark energy is, and what the future of the cosmos holds, continue to be explored. As our understanding of the universe evolves, so too does our sense of wonder and our place within it. We have only begun to scratch the surface, and with each new discovery, we draw closer to understanding the profound mysteries that lie at the heart of the cosmos. Ultimately, the search for answers to these unsolved cosmic mysteries is more than just an intellectual pursuit. It is a journey of discovery that connects us all as humans, united by a shared curiosity about the universe. These mysteries compel us to ask questions that push the boundaries of knowledge, that challenge what we think we know, and that inspire us to explore not only the cosmos but also the very nature of existence itself. The universe remains an ever-present enigma, one that continues to captivate and inspire us with its depth, complexity, and beauty. The pursuit of these answers is not just the domain of scientists. It is a human endeavor, one that reaches to the very core of our nature. Chapter 8: Philosophical Reflection. The meaning of it all. Humans and the cosmos. From the moment we first looked up at the night sky, humans have wondered about their place in the universe. We have marveled at the stars, contemplated the vastness of space, and pondered the mysteries of existence. The universe, in all its vastness, presents us with questions that extend far beyond the realm of science. These are questions about meaning, purpose, and our place within it all, questions that probe the very essence of what it means to be human. As our understanding of the cosmos has grown, so too has our awareness of the profound philosophical implications of our existence. The search for knowledge has not only been a scientific pursuit but a deeply existential one, asking us to reflect on who we are and what our role is in the grand cosmic tapestry. We've made incredible progress in exploring the universe, from sending probes to the outer reaches of the solar system to detecting planets around distant stars. Yet, as we continue to expand our knowledge, we are confronted with questions that remain tantalizingly out of reach. One of the most enduring and fundamental questions is, what is our place in the universe? For centuries, humanity believed that Earth was the center of existence. This geocentric view of the universe dominated for millennia, only to be replaced by the heliocentric model, which placed the Sun, rather than the Earth, at the center of the solar system. However, even with this paradigm shift, we remained the dominant force on our planet. But as our understanding of the universe has expanded, we have come to realize that Earth is but a small speck in the vastness of space, orbiting an ordinary star in one of countless galaxies. This humbling realization has led many to consider the larger questions. Are we alone in the universe? Is life on Earth unique? Or is there the possibility of life elsewhere, scattered across the billions of stars and planets that populate the cosmos? These questions have occupied the minds of philosophers, scientists, and thinkers throughout history, and they continue to drive much of our exploration of space. The discovery of exoplanets, planets that orbit stars beyond our solar system, has opened up a new frontier in this search. Thousands of these planets have been discovered in recent years, many of them located in what is known as the habitable zone of their stars, where conditions might be right for liquid water to exist. This has raised the possibility that life, in some form, might be common throughout the universe. After all, if planets like Earth are common, could life too be common? Perhaps life is not as rare and exceptional as we once thought. On the other hand, we have yet to find definitive proof of extraterrestrial life, and this raises profound questions about the uniqueness of life on Earth. Could it be that Earth is the exception, the only place where life has emerged in an otherwise lifeless universe? If life is so rare, what does that say about the conditions necessary for life to thrive? And, more importantly, what does it mean for our understanding of our own existence? These questions are not merely theoretical, they have implications for our understanding of biology, chemistry, and even philosophy. The search for extraterrestrial life is also closely tied to the field of astrobiology, which studies the potential for life in extreme environments. On Earth, life exists in some of the harshest conditions imaginable, from deep-sea hydrothermal vents to the frozen tundra. If life can thrive in these extreme environments, it stands to reason that it might also exist in similarly harsh conditions on other planets or moons. Scientists are particularly focused on the search for microbial life on Mars, Europa, and Enceladus, moons of Jupiter and Saturn, respectively, that are believed to have subsurface oceans where life might exist. This search is not just about finding life as we know it, but also about expanding our definition of what life can be. But what if the answer to the question of life in the universe is not simply yes or no? What if the true nature of life is more complex and diverse than we can even begin to imagine? The idea of panspermia, for example, suggests that life might not have originated on Earth at all but could have been brought here from elsewhere in the universe, perhaps on a comet or asteroid. This concept challenges our traditional understanding of life's origins, and raises the possibility that Earth is not the cradle of life, but rather a stepping stone in the vast cosmic journey of life. As we search for answers to these questions, we also find ourselves confronting deeper, more philosophical considerations about the nature of the universe itself. The fact that we exist in the universe, able to observe it, understand it, and ponder our place within it, raises profound questions about consciousness and the nature of reality. How is it that we, as conscious beings, are able to comprehend the vastness of the cosmos? What is the relationship between our minds and the universe around us? Some philosophers argue that our ability to understand the cosmos is evidence of a deeper connection between us and the universe, while others suggest that it is simply a product of evolutionary processes, a byproduct of our brain's ability to solve complex problems. In some ways, the search for extraterrestrial life is a search for meaning. If we are not alone in the universe, if life exists beyond Earth, it would be one of the most profound discoveries in human history. It would not only change our understanding of biology and the nature of life, but also have profound philosophical implications. It could alter our perspective on ourselves, on the universe, and on our place in the grand scheme of things. But until that discovery is made, we are left to wonder. Are we truly alone? Or are we just one small piece of a much larger cosmic puzzle? This mystery also raises questions about the future of humanity. If we were to find intelligent life elsewhere in the universe, what would that mean for our future? Would we be able to communicate with them? Would we share common values? Or would we be completely alien to one another, both culturally and biologically? These questions challenge our ideas of what it means to be human and what it means to be part of a larger cosmic community. At the same time, these questions force us to reflect on the nature of the universe itself. What is the ultimate purpose of the cosmos? Is the universe simply a vast collection of random events? Or is there some deeper meaning, some cosmic order at work? These are questions that have occupied the minds of scientists and philosophers alike. And while answers remain elusive, the search for understanding continues to push us forward. As we continue to explore the cosmos, we face not only the mysteries of space, but the mysteries of ourselves. Our place in the universe is still a puzzle, and each new discovery only raises more questions. But perhaps that is the beauty of our existence. Our endless curiosity, our unyielding drive to understand the unknown, and our relentless pursuit of meaning in a universe that seems so vast and incomprehensible. Whatever the answers may be, the journey of exploration, whether through science, philosophy, or the search for life, is one that will continue to shape our understanding of the universe and our place within it. The cosmos is full of questions, but it is also full of wonder. And that, perhaps, is what makes the search so incredibly compelling. Concluding thoughts. As we near the end of this journey through the vastness of the universe, we take a moment to reflect on all that we've explored. The cosmos, with its countless stars, planets, and galaxies, has revealed a picture of unimaginable beauty, complexity, and mystery. We've traced the origins of the universe, from the cataclysmic eruption of the Big Bang to the formation of galaxies, and have ventured into the uncharted territories of dark matter and dark energy. We've gazed at the possibility of life beyond Earth and the vast stretches of space that remain hidden, waiting to be understood. But even with all the incredible discoveries we've made, the universe continues to surprise us, offering more questions than answers. It beckons us to look deeper, to ask more, and to never stop exploring. What lies beyond the stars? What forces shape the cosmos that we have yet to comprehend? The universe is a living, breathing entity that is constantly evolving, expanding, and shifting. Every discovery we make only serves to spark new questions and reveal more layers of its complexity. Yet, despite the infinite unknowns, we also begin to see a pattern, a structure, and an order in the vastness. In its beauty, there is a method. In its chaos, there is a quiet rhythm that unites everything. Reflecting on this grandeur, we come to realize that the universe is not just a vast expanse of space and time. It is a story that we are part of, that we help shape with every question we ask, with every discovery we make. The universe is a journey without end, one where each new piece of knowledge propels us forward and brings us closer to understanding our place within it. But perhaps just as important as the discoveries we make are the questions themselves. It is in these mysteries, these gaps in our knowledge, where the true beauty of the universe resides. It is this mystery that inspires awe, that fuels our curiosity and pushes us to look beyond the horizon of what we know. In the quiet corners of the universe, in the darkest black holes and the most distant galaxies, there are still stories waiting to be uncovered, waiting for the right moment to be understood. We are, after all, explorers of both the physical and the philosophical. Each discovery adds to our shared story. Each step we take out into the cosmos is a step towards understanding not just the stars, but ourselves. The majesty of the universe is not just in its infinite expanse, but in its potential to reveal things about our existence, about the fundamental laws that govern life, time, and space. As we reflect on the immensity of the universe, we are reminded of the humbling nature of our existence. Our planet, our solar system, our galaxy, they are but specks in a vast, ever-expanding universe. Yet we have the ability to wonder, to ask, and to understand. And that is what makes our journey so extraordinary. It is not just about finding answers. It is about embracing the mysteries, appreciating the beauty, and recognizing that each discovery, no matter how small, adds a new layer to our collective understanding. In the grand scheme of the universe, we may be tiny, but we are not insignificant. Our thoughts, our curiosity, and our drive to explore make us unique. The beauty of the cosmos lies not only in its vast, breathtaking expanse, but in the endless possibilities that exist beyond what we know. As we venture into the unknown, whether through the exploration of distant stars or the search for life on other planets, we continue to define our place in the universe, constantly evolving and reaching for the stars. The universe is a story that will never end, and we are its storytellers. From the beginning of time to the vast, mysterious future, we remain part of a larger cosmic journey. And as we look up at the stars, we remember that they are not just distant objects in the sky. They are symbols of the infinite possibilities that await. The universe, with all its complexities and mysteries, is ours to explore, to understand, and most importantly, to marvel at. The questions we've asked today may not be fully answered tomorrow, but the journey to understanding will never cease. It is a journey that will continue for as long as there are curious minds, those who look up at the sky with wonder and ask, what lies beyond? And in that question, we find the true beauty of the universe, its endless possibilities.